Eu achei que era a banca. Não tinha me tocado que era a entrega agora.
Tá tudo certo?
Uhum.
Pode começar, Michael? Thereza, acho que a gente vai começar.
Ops.
Hello. Good morning, everybody. Welcome back to the third day of the school. We hope you are enjoying your talks, lectures. We still have much more in the program. Be prepared. Today we will start with our first speaker, Professor Thereza Paiva, from Federal University of Rio de Janeiro. She had a postdoc in the University of California, Davis, United States, and another one in the Federal University of Rio de Janeiro, UFRJ. Since 2010, she is professor in the same institution, UFRJ. Her main research fields are superconductivity, strong correlated systems, and fermions in optical lattices. She also carries out important extension activities, including a project for women in science. Thank you, Thereza, for accepting our invitation. Please, I think you can start now.
So thank you very much for this invitation. I am really thrilled to be in person somewhere, so it's great to be. Can you hear me all? I think the mic is working now. I'm really happy to be able to interact with people once again, so thank you very much. So I'll be speaking today about the dimensional crossover in the attractive Hubbard model. And first of all, I want to acknowledge my collaborators. This is an in-the-house work. People from UFRJ, the Federal University in Rio. So Rodrigo is a student, Nathanael and Raimundo are colleagues. And part of this work is in archive, and there is some new things that are follow-up from that. So the summary of my talk, I'll start with a motivation why we want to study the dimensional crossover and the attractive Hubbard model. And then I'll try to motivate the study of the Hubbard model. And here I'll put together the repulsive, imbalanced, attractive Hubbard model. Then I'll speak about the temperature scale and topological phase transition, and what I think is mostly likely to be of interest of this audience, which is the BCS-BEC crossover in this model, and then dimensional crossover, and what we are looking forward in the future. So Randy spoke yesterday about two non-identical twins, lithium-6 and 7, and there are also potassium-39 and 40. And I think everybody here knows pretty much well that bosons and fermions are different and they behave very differently when trapped. But here I want to go a step further and also talk about periodic potential on a trap. So on top of the trap, which could be optic or magnetic and have a parabolic shake as the one I've shown, or a compensated as the one Randy uses. Here we're discussing what happens when a periodic potential comes in, and this can come from counter-propagating lasers or an holographic mask. And the idea here is to study many-body physics with cold atoms. And Vanderlei yesterday, now he's awake, asked why do we want to keep studying quantum magnetism? And it's not only to study quantum magnetism that we are looking into the systems. There are other things that are interesting, such as exotic superconductors, quantum criticality, topology, and disorder and entanglement. So the list is long of the things we can do in many-body with this platform. But speaking about geometry, this is one reason I think that the quantum magnetism field is very alive, is that we are able, we, the experimentalists, not me actually, to change the dimensionality and the geometry of the lattice. And it's not something like, oh, we've done everything for the square lattice, let's do now the honeycomb. When you switch from square to honeycomb, you change the not only the geometry, but the dispersion relation from parabolic to linear, and everything changes. And when you go to the Kagome lattice or the triangular lattice, you build in frustration on your system, and everything changes once again. So there are many, many different aspects that come about when you change either the geometry or dimensionality or density or spin imbalance, as I'm going to show a little bit today. And one reason why this field is so much alive is because of the high TC superconductors. Though they have been discovered in '86 or synthesized in '86, there are so many open questions that remain. And the main one is the $1 million questions. What is the glue that makes this material superconducting? So this is a very much open question in this field, and very important questions. And everything here happens in the vicinity. So this pink region here is an antiferromagnetism region. This blue dome here is where superconductivity takes place. And this green region here is discussed a lot, like, do we have a spin liquid or some kind of disorder or charge ordering? So everything happens in the vicinity of an antiferromagnetism. And so this is important to understand the interrelation between all this that's coming about here. So the idea is that it's pretty much the same physics that happens in these materials with strongly correlated fermions on optical lattices and the materials where superconductivity happens. So experimentalists are trying hard to emulate the strongly correlated Hamiltonians in optical lattices. And the one that is the most simple, and as Randy once again yesterday mentioned, deceivingly simple Hilbert model, because there are only two terms, one which gives the hopping from one side to the other in your lattice, and here we are only considering near neighbor hoppings, and the other terms makes you pay an energy U that is set by the Feshbach resonance and can be changed whenever two different fermions meet on a lattice, and we can only have fermions with different spins. And there is this also term here, the chemical potential, that allows you to bring in and out fermions on your system. So this simple model has inbuilt into it, in it a competition between the repulsion that makes the system want to localize and the hopping that makes the system want to delocalize. And it's known that at half filling, when you have 1 electron per site or 1 atom per site, we have a Mott transition that leads the system into an insulating state, and as you lower the temperature even further, you go into an antiferromagnetic state. So this is very well known and has been seen in optical lattices experiments. Here is this beautiful picture from Greiner group that has taken a shot of his 2D lattice, and you can see each blue dot here is an atom on an optical lattice, and it's very clear here that we do have a full region, a ring, a circle with 1 atom per side here. We have this ring, and here in the middle, because of how imaging is done, it's actually double occupation, but it looks empty because the atoms are ejected. But here we can see a Mott region, so it's been very well probed in these experiments. And here we see the experiment also that Randy has shown yesterday, where antiferromagnetism was probed with Bragg scattering. So this has been observed. And the latest achievements in this field come from a huge progress in imaging. So back in 2009, Bakker was able to do atomic resolution for boson. So in this image here, each green dot is a single atom. And this made a huge impact on the field. And it took a few years until 2015-16 until people were able to do the same for fermions. So here are different groups and their images, people that like working with potassium, people that prefer lithium, but the quantum gas microscope is now well established for fermions as well. And so one thing that's interesting, there are many works that use this technique to probe the systems, but one I like to highlight here is this by also Bakker group, in which they have probed a spin-imbalanced two-dimensional Fermi-Hubbard model. And in this, what they did, they have a synthetic magnetic field, and so they have more fermions with up spins than fermions with down spins. So the Hamiltonian is very similar to the one we had before. We just add a term that imbues a Zeeman field. And with this, we have some polarization that can be changed within the experiment. We have more ups than down, and he was able to probe spin-spin correlation functions along the z direction, in the direction of the field, and perpendicular to the field. And they are not the same. So here, the big circles are experimental data, the small dots are quantum Monte Carlo data, and the line is numerical linked expansion data. And we can see that clearly correlations along the z direction and within the plane are different. And in the bottom panel, we see the anisotropy between the near neighbor and next near neighbor spin correlations. And with this, what we see is that the spins, when you put a magnetic field, the spins get canted. They lie down on the plane. And instead of having an isotropic magnetism, we have this canted phase. And why is it important? Because we break SU2 symmetry. And so for the symmetric system here in this region and the fully magnetized system, as we are in a SU2 symmetry, we have the temperature goes down. And I'll come to this in a moment. But when we break the symmetry, we have an order parameter that has only two components, and we can have this Kosterlitz-Tauss phase, which is highlighted here by this dome. So we enter a topological phase, and we have a quantum phase transition at a non-zero temperature here in this dome. So it's different, and it's worth analyzing what's going on here. And just to highlight the experiments, so theory works in this experiment sometimes as a thermometer. They don't know the temperature, but we provide them, data for different temperature, and in comparing temperature and experiments and theory, they know that the temperature, and so they are here well above or a little above this dome. So the experiments have not reached this phase yet, but the phase is there. And so now I come with a comparison between the repulsive and the attractive Hubbard models. This has been known for a long time, that if you take this symmetry transformation, you do nothing with the upspins, they remain the same, but you take a downspin and you turn it into an uphole. And you do this transformation here. And in doing so, you change the repulsive Hubbard model in the presence of a Zeeman field into the attractive Hubbard model in the presence of a chemical potential. So at zero field or zero doping, these systems are symmetric, and you are in this SU2 phase. But either when you put a field in one case or dope in the other case, they are not symmetric. And what happens when you do that, if you work out the transformation, you turn SZ correlations into charge correlation, and the up and down spins or in-plane spins you turn into the superconductivity correlations. And so you mix charge and spin when you go from one to the other. And there was this experiment last year, or 2 years ago now, that was really, really interesting, where they have actually probed this. So this is from Cole's group, and this is, they changed the interaction strength Here it's negative U, here is positive U, and one is the charge sector, the other is the spin, and they probe this transition. It's a very beautiful experiment. And so with this, we think the attractive Hubbard model is worth studying. It's interesting, this model has been, discussed since the early 80s or around that. And on the early days, it was a very phenomenological model. Oh, what happens if we just put in some attractive interactions and see what happened? It was studied to understand pair formation and superfluidity. But now with cold atoms, it becomes a realistic model, as I have seen in that experiment that I've just shown. And it's just a matter, you tune in your Feshbach resonance and you turn repulsive into attractive interactions. So you can actually study this model. And the reason why it is so interesting is very similar to the reason why the repulsive Hubbard model with the field is so interesting. Because of the Mermin-Wagner theorem, it's a very general theorem. And what it says is, like in 2D, whatever happens to your system depends on the number of components of your order parameter. So when we broke the SU2 symmetry, we have this number of components on your order parameter. So if D is the dimension of your system is bigger than the number of components, then you can have a critical temperature that's different from 0, and that's what we see in 3D. But if the dimension is smaller than the number of components, then the critical temperature is pushed to 0, and that's what happens when we are in this SU2 limit. But here we can have the dimension being equal to the number of components, which is 2 in this case, and we have the Kosterlitz transition. And this can be achieved either on a repulsive model with a field that breaks the anisotropy between Z and X and in-plane correlations, or in the attractive Hubbard model with doping, and we have a superfluid state. So there are experiments for both cases in this platform of optical lattices. So this is Martin Zwirlein's group, where they have studied the attractive Hubbard model, and that one is the Backer group that I have shown previously, where they have studied the repulsive Hubbard model with the field. And it's interesting, here the experiments are up above, and what really happens, the ordered phases is below, but it's the same physics, the Kosterlitz transition. And so what happens when we have attractive interactions in Fermi systems has been the subject of interest for a long time. And here is a figure from a review from Mohit Randeria, and this is showing what happens in the continuum case. So this blue phase here is the superfluid phase, where we have superfluidity. And here we have above the superfluid a normal Bose liquid in the side where interactions are stronger, and here normal Fermi liquid. Here we do have some pseudo-gap phase below this T star, which I'll discuss later. But what's really interesting here is when interactions are very strong, we expect a BEC phase where we have very tightly bound pairs, and when the interaction is weak on the other side, I'll show a cartoon later, but we expect the pairs to be loosely bound. And so this is for a continuum system without the lattice, but with the lattice, this is a picture that has emerged in the 90s. This is a very well-known review. We do expect something similar. We do have this superfluid region here. It just is different than in the continuum, because in the continuum we don't expect it to drop in temperature, and here it drops as T squared over U. And here we have a phase with uncorrelated pairs, and here we have a normal metal, and to this side we have a Fermi liquid, and this dashed area is a pseudo-gap region. And so this is a more recent attempt on the phases and with not a cartoon but actual values. So here is the superfluid region. Here is a zoom because it's squeezed down, and so it's hard to see. But here it's also an interesting phase, which is the degenerate phase. I'll also come to it in a moment. But the idea is if we have strong correlations, we expect to have preformed pairs that condense at low temperature. But if we are in the side of the transition, what we expect is that the pairs form and condensate at the same time. So the transition is different whether we have strong or weak correlations. And this is where we come to this BCS-BEC crossover. This is a cartoon from this review here. And it's interesting, the title of review is not on condensed matter or atomic physics, it's some particle physics, but it's the same thing, the same physics that's going on. So if we have a very weak interactions, the pairs are large and very weakly bound. And if we have very strong interactions, we have very localized pairs that are, condensed, and then they are formed before, and as you lower and lower the temperature, they entered ordered state. So this is where we discuss what we've done. So we've studied the 2D attractive Hubbard model. And one thing also that's interesting to mention, we use numerical methods to study the system. We use quantum Monte Carlo. And usually when we do simulations with quantum Monte Carlo, we study fermions, so we are subjected to the so-called Fermi sign problem, which makes it hard to analyze what's going on if we are at lower temperatures, and sometimes we have so bad sign that we cannot say much on the system. But when we are dealing with the attractive Hubbard model, we don't have a sign problem. So that's all we want when doing theory, is being able to reach all the temperatures and densities. So we start by looking at pair formation. So we look at this pairing correlation functions. So we studied the probability of forming a pair in one site and how is it correlated to a pair in a site that's far away from the original site. So here we are looking pairs across the diagonal because it makes it further and further distance. And so what we see here, this black line is for beta is the inverse temperature. So this is for high temperature, and the pairs are not correlated. But as we decrease the temperature, we see that this pairing correlation stabilizes and doesn't fall anymore. So we are seeing some indication that we are entering an ordered state. But to find the critical temperature, as we are in this Costa-Litals transition and in this universality, what we do is we probe this finite size scaling, taking into account that we are in this type of transition. So we have this exponent eta that's known to be 1/4 for this kind of transition, and we do this collapse of data, trying to, we change both TC and A and try to change them so that we have a data collapse, and this leads to this critical temperature. This is not a very practical way of extracting the critical temperature. So we also, I think I removed the other plot. So, but we do this also by renormalization group. So we do this for a given value of U, a given value of density, and then we build a phase diagram such as this. So this is the transition temperature as a function of the interaction strength, and the different data here are for different densities. And this is the same data, just plotted some other way, the transition temperature as a function of density for some different values of U. And it's interesting to see that, here for U around 5 and density around 0.8, it's where our maxima is. This is just a nice way of showing this plot. And this is something interesting to tell the experimentalists, because if they want to reach the ordered phase, they don't want to go to the very, very low temperatures. So what is the temperature and density that maximizes the critical temperature. So where should they do their experiment to make it easier to observe? Because going to lower and lower temperature is harder and harder. So their life is easier if they are around this region here, around U5 and 6, and around this density 0.8, 0.7. So this is something important to let them know. And so, given that we now know where the critical temperature is, there are other scales, temperature scales that are interesting. One of them is the pairing temperature or the pseudogap temperature. So if we, this is once again like a broad general phase diagram for the superconductors. And we do know that for a density, a doping density around, in between the antiferromagnetic and the superconductor, as we decrease the temperature, we enter this phase, which is called the pseudogap phase, where we do start to have some pair formation. So can we tell something about where this boundary is? And one way that has been well established to probe that, so here our experimental data, is just where do we start to have singlets. And so singlet formation is one probe for the system, and what we usually do is pretty much the same as the experimentalists do in this material science, not in cold atoms, which is looking at the susceptibility. So we say that where the susceptibility is peaked is where we start to have the pairing and the pseudogap region. And so we define the pairing temperature this way. Another very interesting temperature scale is the degeneracy temperature. So for one way to define this is looking into the fugacity. So we do know that for a classical system or at high temperature, the fugacity goes to 0. It's much smaller than 1. And in the extreme quantum limit, the fugacity is high and it's much bigger than 1. So where it is around 1 is where we set this degeneracy temperature, where the system becomes to act in a quantum way. And one way to probe that is just we compare the chemical potential to the temperature, and here we subtract the bandwidth and the Hartree shift. And so here is the fugacity, and here where I have set this black stars is where for the different values of U, they cross the chemical potential. So we are able to set also the scale. And here is a plot with the scales for different densities. So we see as we move doping, we change all the temperatures. So in red, we have the superconducting, the critical temperature, and I had to multiply it by 4 because it's so tiny, it's hard to fit in the same plot. And in black, we have this degeneracy temperature, and in blue, the pairing temperature. So the relation between pairing and degeneracy changes as we change doping. One way of characterizing the BCS to BEC crossover is looking at the double occupancy. So as I said before, when we have tightly bound pairs, we are in the BEC phase. And when we have loosely bound pairs, we are in the BCS phase. So if we look at when the pairs form and how they form, it can give us some hint of what's going on. So here at small dopings, here is different histograms of the double occupation. So if we have a strongly peaked system, double occupation in 0 and 1, it means we have either the system, the sites are either empty or doubly occupied. And if we have only a peak in 0, it means we have very little double occupations. And here, I've set some little marks to start to show that as we increase U with a given density, we start to see this peak developing here, and we start to see double occupations, which is the double occupation at 1 forming in one case as we increase the attraction. And if we are at a higher density, we have more atoms to form pairs, and this double occupation starts to form early. So we have a crossover. This is not a sharp transition, so it's hard to say this is where it happens, but we say that since we start to see this peak forming around U equals 4.5, and here the peak starts to form earlier at 3.5. So we see this crossover forming. And one other thing that's very interesting and not very much discussed when looking at the attractive Hubbard model is Fermi liquid behavior. And this is important to understand. And the idea is when we have a Fermi gas, we only see the particles in the vicinity of the chemical potential participating in the interactions. And here in the Fermi liquid, we have a much larger scale of interactions in energy. And we can define Z and as the size of the jump here in this linear, this straight line here. And so if this is close to 1, then we have a Fermi liquid. And if we see that this is slowly, as in here, and continuously changing, then we have a non-Fermi liquid. So, so the behavior of the self-energy tells us important things, whether this is in a Fermi liquid or non-Fermi liquid regime. And we can extract this from quantum Monte Carlo simulations. So we extract this by getting the Green's function. And another probe to see if we are in a Fermi liquid or non-Fermi liquid is looking at n of k. So the number of particles with a given k vector. And here, the red line is what happens in the non-interacting system. So this is the Fermi surface of a non-interacting attractive model, Hubbard model, with this density. And we see that for small u, what happens is we have a very similar filling of the states as in the non-interacting case, and the systems are, the Fermi surface is filled inside, and the states outside of this Fermi surfaces are empty. And so this is pretty much, we can say very clearly that this behaves like a Fermi liquid. But as we increase the interactions, what we see, it gets lighter here, so it gets unoccupied here, and more occupied outside the Fermi surface of the non-interacting system. So when we reach this state here, we are clearly not in the Fermi liquid behavior where the states inside the Fermi sphere or surface are filled and outside are not. So we can use this to probe also the Fermi liquid, non-Fermi liquid change as we increase the interactions. And here is also the self-energy. The marked line here is the critical temperature. So below the critical temperature, it doesn't make any sense talking about Fermi liquid, non-Fermi liquid. It's a superfluid, and that's well established. But we see that for strongly interacting systems, whereas EK is smaller, we do have heavier particles, and heavier particles tend to interact more strongly. So now I finally come to dimensional crossover. This is work in progress. And so the idea is, going back once again to the Mermin-Wagner theorem, I've shown that we can have a Kosterlitz transition in the doped system, but when we are here at the symmetry point, the critical temperature has to be 0 because we are in 2D. So what happens if we are not in 2D anymore, and what happens if we are slowly change the dimensionality? So how can this be made? So we can think we have separate planes. So when these planes are very separate, I try to draw them separately here. We don't have hopping from this plane to this plane, and the hopping along the z direction is 0, so we are in a strictly two-dimensional system. And here, on the other opposite, when these planes are close together and the hopping from this plane to this plane is the same as the hopping for sites in between in the same plane, then we are in the actual three-dimensional system. And when we are like in between, the planes do connect, but they don't connect the same way as atoms in the same plane, then we are in between 2 and 3D. And so what happens to the critical temperature? We know that here it has to be 0. We know that here it has to be non-zero. How does it evolve? And this is something, you know, it can be probed in an experiment. You just have to use the lasers in the z direction with a different wavelength as the lasers that set the lattice on the plane. So just to mention that this is a theoretical work with which Randy is one of the co-authors as well, in which he studied the repulsive Hubbard model with hopping in the plane being the same and perpendicular hopping being different. He called it T perpendicular. And one thing that's really interesting here is in this work, we were not able to characterize the critical temperature. So here, T star is the temperature at which the specific heat has a peak. And it's clear to see here, this is for half-filling system and different values of the interaction strength, all of them repulsive. And we see here T is equal 1, which is the strictly 3D. And as we decrease, it's pretty much linear. And here at T perpendicular equals 0, there is still a peak at a critical, at a temperature that is non-zero. So the specific heat is not a good probe for transitions, especially in 2D. It has been well known for many years that the specific heat has a peak at low temperature for 2D, and it's known that it's not a critical temperature. So it's just the temperature where correlations grow strong, but that doesn't mean the system is ordered. In fact, it cannot be. So here we do the same study in 3D, and so we have hopping for particles in the plane, we are calling it T, and hopping for planes in between planes when we are calling it TZ. And we are setting our energy scale as to 1 for atoms in the plane, and the hopping in between planes we are calling TZ, and it's going to go from 0 to 1. And one way to probe this is to look at the correlation ratio, which is RC we define here. So this is the correlation, the pairing correlation function I've studied before. And here, if we define this correlation ratio as 1 minus the pairing with the, we see a plot here as a function of inverse temperature, and where we see crossings here is where we would like to call it our phase transitions. And here, let me just call your attention. We have a small system sizes, 6 by 6 by 6 and 8 by 8 by 8. And we also have non-cubic lattices, 6 by 6 by 8 and 8 by 8 by 6. And looking at this, I find it hard to look at the transitions. So in between this region is where most line crosses. But another possible way of looking into this is looking at the scaling. So we go back to where we've seen before. So we have L, which is the system size, to the -2 times the pairing correlation function as a function of beta. And here, as we don't have cubic lattices, we have some different lattices. There are different ways of getting what we call L, and these 3 here are just different attempts to do so. And I like this 2 here better because I think it's clear that when we have 6 by 6 by 6 and 6 by 6 by 8, they get together here, and 8 by 8 by 8 and 8 by 8 by 6, they get together here, so they are close to each other, and it's clear that the crossings are here as they are here, so I've marked them. So for this particular hopping, I'm saying that the transitions is between 3 and 3.2 in beta, so we repeat these for other hoppings. I'm not going to bore you with that. So this is our final phase diagram where we see that we start as a critical temperature around 0.35, and we go to 0 as we decrease the hopping, and we move from 3D here to 2D here, and this is a dimensional crossover. So I come now to the conclusions. So the degeneracy temperature that we were able to calculate, they probe the quantum behavior of the system. They are important in which we start to see quantum behavior taking place. The pairing temperature is also very interesting because they provide information on the, not only on the pairs, but also on the Fermi liquid, non-Fermi liquid behavior and momentum distribution. And we can see with that a change from strongly bounded pairs to double occupation distribution and weak boundary pairs. The critical temperature has a maximum around 0.5, U equals minus 5T, and this density here in 2 dimensions. And in the crossover from 3 to 2, we only studied U over T equals 8. The rest is on its way, but we are curious to see what happens as we change the interaction strength. And also what we want to look, besides looking at this case where we don't know we have to go to 0 as we decrease the dimensionality because we are on the SU2 symmetry, we want to study it away from half-filling and maybe see if there is some region of densities or interaction strength where being in between densities actually helps increasing the temperature. So with this, I want to thank you. And before I open up to questions, I just have to, it's stronger than me and I have to make a remark on that. I want to, I noticed that I am the only woman speaking this week, and I check it next week, there is like 1 or 2. It's not like, oh, all women and 1 man, and we have balanced restored. So I've seen during the week small, younger girls, and I don't want you to get discouraged by that. And so I want to tell you that there are numerous women in this field. I am by no means the only one and not the other 2 that speak next week. And so they're either theory and experimentalists and younger and not so young as me. So don't get discouraged. We can do it. So with it, I finish up. Thank you.
Thank you very much, Thereza. And please, questions? Please, Dalila, come here.
Hello, thank
Hi.
you for the talk and the advice at the end. So you talk at some point about an imbalance, a lattice full of a spin imbalance lattice, so you have like an extra up or extra down, yeah? So I was wondering, isn't this like a ferromagnetic state? Like when you have
So it depends on how you change your polarization. If you have a fully polarized state, like you remove all the down spins and you only have up spins, then you're in the ferromagnetic state. But if you're in the completely balanced case, you're in the antiferromagnetic state. And what happens when you polarize the system is not that you turn the system down and some of the particles down, is that the spins get canted in the plane. So that's different from what you would naively expect, that, oh, you have an antiferromagnet and you remove some up spins and now you have more down spins and you have the spins pointing down. So they don't do that unless you fully polarize. What happens is that they cant down and they lie on the plane instead of lying perpendicular to the plane. And this, the first time I saw that, and that's not intuitive at all, but that's what happens. The spins cant and lie on the plane rather than being anti-aligned or aligned to the plane.
So isn't this like the behavior of when you have a ferry transition to a paramagnetic transition? So like you have ordering and then you lose your ordering because of temperature, but in this case you have ordering and you lose the ordering because of...
Yeah, we don't lose the ordering. That's
the temperature is low.
very interesting, because when you are in the non-polarized case, you have ordering only at 0 temperature. So you polarize and you have order at a non-zero temperature, and your order is like the spins fall on the plane and they anti-align on the plane instead of, in the Z direction.
Ah.
So when you are in a polarized systems, all directions are the same, and you can have antiferromagnetism pointing in the Z, in the X, and in the Y directions. They are all similar. But when you introduce this field, you break the symmetry, and the spins like to align on the plane perpendicular to the field. And the critical temperature rises from 0 to a non-zero value, and so achievable in the experiments, not now because the experiments are still in a higher temperature, but maybe in the future or near future, they will reduce the temperature and we'll be able to see this canted antiferromagnetism, which is completely similar to the superfluid state in the attractive case.
Okay. Thank you.
Thank you. More questions? Please, Van der Lee.
It's good to do some exercise.
I have, well, thank you for the nice talk. We've seen so many talks about those phase transitions, but we always learn when good people talk about that. I have 2 questions and a comment. The first question is, many laboratories, they have the microscope where they look, and we don't see a full-filled lattice. We see a lot of empty space. How is that in your model? Do you take that in account, that the occupation is not 100% of the lattice?
So I'm not sure I understand this, so...
I have a lattice that's not complete filled the sides. So you take that in account?
Yeah, so this is what I am showing here is this, not here. So this is, let me show you. So this is the doping of the system. So when we are...
the doping is the doping with vacancies. So if I have in the lattice vacancies and atoms, that's in your, you take that in account.
Yes.
But then there will be an occupation number or nothing will happen. I mean, it's very hard to get the superconductor out of that, right? If I have a few atoms and empty lattice.
So...
where is that in the model?
So I think maybe that's what you're talking about. This N is the density.
Okay.
And it's the on-site density.
So that's the average occupation of each site. Okay.
The average occupation. So if you're in a very empty lattice,
then
your
nothing
critical
happens.
transition temperature is very, very low. And as we
that's
increase the
fine.
density. And here it's not very clear, but when you go to 1, there's this dotted dashed line here. It has to go to 0 again.
So when you have a full occupation,
Yeah.
goes to 0 again.
Yeah, not full, it's like half filling, 1 atom per site, you could have 2. And this is completely symmetric here. If we go from 1 to 2, it's just a mirror reflection.
Yeah, I understand. That's clear now. I did not got all the information from the diagram. The second question is, when you go to 3D, then you have hoppings between, you said in plane, and then between planes. Okay. Are they the same? Or I can have an anisotropy in the system?
So that's the idea. We study the system with anisotropy. So let me, put here. So we can study the case where the system is 3D isotropic and the hopping is the same in plane and out of the plane. And this is one case, but we can study the system as a function of the hopping in between planes and see what happens when we interpolate the 2D case where there's no hopping and the 3D case where the hopping is the same and see what happens. And this is what happens. So
yeah, but I may have interaction but not hopping, so.
no, the system is always interacting.
Yeah, but if I don't allow my exchange between planes,
So
I'm
this
going to
is
have a
this
system
case.
that's very anisotropic.
Yeah, so this is this case where no hopping is allowed between the planes. And this case here is the system is isotropic
okay.
and the hopping is exactly the same in between the planes. And this is the way from going to one to the other. So we interpolated the two-dimensional and three-dimensional case.
Okay, well, now is a question of my own stupidity. Is there any classical magnetism? Why people keep calling quantum magnetism? Is there a classical magnetism?
So, yeah, yes and no. So magnetism is clearly a quantum thing. Spins are quantum, and you can only have magnetism if the spins are quantum.
So why not only magnetism?
Yeah, so it depends on how you model your system. So if you have, for instance, a material in which you have some sort of anisotropy or field effect that it forces the spin to point only along the z direction, you cannot have x and y components, then you are in one class of universality, or you have an Ising model, and this behaves very much as a classical system because you don't have what you have here, which are terms in your Hamiltonian that don't commute with each other and leads to this quantum behavior. So if you have the spins pointing in only one direction because of the symmetries of your system, either not a strong Zeeman field, but lattice field, and this forces you have to.
It's more the approach than the real nature of
No, it's not. It's not the approach. It's like there are a number of systems that behave like an Ising model. And why is it so? Because in the systems, because of crystal field or other effects, the spins only point along the z direction. And so you don't have x and y components, and this is very much classical. And there's cases in which your spin is always on the plane, and this is like an XY model, and this is quantum. And in the three cases, this is also quantum. So this is the difference between classical and quantum magnetism.
Okay. Okay, Eric, please.
So thanks, Thereza, for this really nice talk. So I just have some curiosities. When you talk about Mermin-Wagner, the correlation length into this kind of exponential, can you estimate this correlation length within your system size? Probably it's larger than your system size, so that's why I'm wondering, I mean,
so yeah,
these transitions.
I think I had some extra plots here. So this is how the correlation length goes to. This is the correlation length. It goes to psi to force the, so, and it goes this way. So we could, in principle, see how it falls and make a plot. This is of how the correlation length falls. But we haven't probed that.
Okay, I was just wonder because it may be relevant in experiments as well. I mean, maybe it's larger than the system size.
Yeah.
That's why I'm wondering. So when you show that nice pictures of the effective mass, and you showed you are losing your Fermi liquidity, so do I know how this M star goes with U in the large U's? It's like linear or something like this?
So sorry, what?
How the effective mass behaves with U. So you showed how it goes with T. So if I sit on like T point, like 0.2, how does it behave when I increase U? Is it linear with U or something different?
Oh,
effective mass.
so you're asking how does it change with you?
Exactly.
We haven't probed here, but you can kind of guess looking at, so there's this region around here where it's linear, because the points are evenly
Yeah,
spaced,
exactly.
but here it's not.
Yeah,
So it does change with temperature whether it's linear or
Sure,
not,
sure,
and
but-
we have not probed it, so maybe this is something
Yeah, because
interesting we could
yeah,
do.
that would be nice because, I mean, you know the large U limit. I guess it's linear. I mean, you can do perturbation
Mm-hmm.
here. So that's why I'm asking that could be something interesting.
Yeah.
Of course, it has to be at low T. So, and one last question. When you do your finite size scale for the cubic system, did you try 4 by 4 by 4?
Yeah, so I have a problem with 4 by 4 by 4 because it has very many symmetries and it looks like a 2 by 2 by 2 by 2
okay.
and it behaves very differently and is plagued with system size effects.
I see.
And so I asked Rodrigo not to do it, but I told him maybe doing 4 by 4 by 6 because this already breaks this symmetry, maybe it's worth a shot.
And do you know why the harmonic average for the L is better than the geometric average? I mean, why you like it more? Do you know why?
Sorry, I couldn't understand.
When you calculate the effective system size, you do the harmonic average. I mean, you say it works better than the geometric average. I mean,
Yeah,
do you know why? I mean, do you have a
No.
feeling?
So I have to tell you that these results came in like Monday. So we haven't had the time to think thoroughly about that. And we certainly want to understand why and have other system sizes and see if these non-cubic lattices help us or not.
Thank you, Eric. Oh, Lucas, I think you still have opportunity for the online. Oh, okay. Then I call you, sorry. Okay, have some questions in the chat.
Oh, okay.
I like to give the opportunity for the online participants too. And then, first one from Raul Teixeira. He wants to know what is the reason to call Fermi liquid by liquid? Why you call it by this, and if it's related to the energy distribution of the system?
Sorry, I didn't understand.
The Fermi liquid, why you call liquid, and if it is related with the energy distribution of the system?
So Fermi liquid is a term that is very, I would say, popular in condensed matter theory, and it comes because of when the system obeys the Fermi liquid theory, it has this some expected behavior. So what happens to the resistivity and what happens to the conductivity of the system. And one thing that is happening when we do have a Fermi liquid, we have this jump here in n of k. So this is a term that describes that the system obeys the Fermi liquid theory. And it's not because it's liquid, it's because it doesn't behave as a gas anymore. And the particles interact, but it doesn't change very much from the non-interacting system. And we can still learn many, many things from the non-interacting systems from if we're in this Fermi liquid region.
Okay. Our second question is from Jacopo D'Alberto. He wants to know what kind of technique, quantum Monte Carlo technique, did you use in your simulations?
So I completely run over by that. I don't think people are usually interested in the details of the calculation, but I use determinantal quantum Monte Carlo, or sometimes people call it auxiliary field quantum Monte Carlo, but it's well established, and I guess that's it.
Okay, the last questions in the chat is from Vinicius Pedroso. He wants to congratulate you for the talk and ask why Fermi sign problem disappears in attractive cases even away of the half filling.
So that's interesting because this is how we do the decoupling. When we do quantum Monte Carlo this way, we use an auxiliary field that changes the 2D system into a 3D with some Ising field where we do the quantum Monte Carlo. And the way the Hubbard-Stratonovich breakup is done, when we have repulsive interactions, we use one kind of breakup that uses spin up and down. And when we do this with the attractive interactions, we do it some other way. And there are different approaches to quantum Monte Carlo, and one thing people are trying to do is like using different breakups to see if the sign goes away in some regions. And one thing I should call your attention maybe is that if we place a Zeeman field in the attractive case, we get back a sign problem. So we are just lucky to be in a region where this is not relevant.
Thank you, Thereza. Lucas, please. Sorry.
Thank you for the very nice talk. So two-body scattering is pretty different in 3D and in 2D to the extent that it's much easier to define the BCS, BC crossover in 3D than in 2D. So when you play with the dimensionality, the last part of your talk, is it possible that, for example, you start on the, I don't know, BEC side in 2D, and then when you go to 3D, you're actually in the BCS side, things like that?
Yeah, so that's a very, very interesting question, and thank you for pointing us to that. So as you can see, this is a ingoing project. We are not done with that, and one of the things we can certainly look at is what happens to the crossover between BCS and BEC as we change dimensionality. So it might happen, we were like first focused on the critical temperature, but if we look above, we might have this, this transition from BCS to BEC without changing either U or density, but changing dimensionality. And that would be super interesting to see. So if we think of a case where we approach and bring the planes apart and we go from one case to the other. So that's something we really should look at. Thanks.
Thank you.
Thank you very much, Thereza. A lot of questions.
Yeah, great.
Yeah. Thank you, Thereza.
Thank you.
Congratulations.
Began.
Oops. Okay. Good morning, everybody. So I'm here. I have the honor to introduce Professor Amir Caldeira. He's give us a series of 3 lectures on macroscopic quantum phenomena in condensate matter system. He's graduate and he has his master's degree in physics from Pontifícia Universidade Católica do Rio de Janeiro, and he had also his PhD in physics from University of Sussex in 1980. Professor Anthony Leggett was his advisor. He has experience in theoretical physics, focusing in condensate matter physics, and acting mainly on quantum dissipation, microscopic quantum effects, and low-dimensional electronic systems. One of his most known work is the Caldeira-Leggett model. That is one of the first and the most important studies of the currents in quantum systems. He's full professor at Unicamp and member of the Brazilian Academy of Science since 2000, and commander of the National Order of Scientific Merit. So, Professor, thank you very much for being here with us, and we can start. Thank you.
Good morning. Good morning, all. Can you all hear me?
Yeah. Yes, you can start, please.
Okay, I'd like to start thanking you for your very kind words of introduction. And I'd like to thank the organizing committee for having invited me to come to this event. And I'm quite happy to participate in this school. And so let's start with the subject of my 3 lectures, which is macroscopic quantum phenomena in condensed matter systems. Actually, it's a very specific family of condensed matter systems, namely I'm going to address this issue in superconducting systems. But of course, it can be extended to many other macroscopic systems. And so these are the outline of the lectures. The first one, I will introduce some elements of superconductivity. I'll talk about superconducting devices, and I will introduce the idea of macroscopic quantum phenomena. And the second lecture, I will talk about something which is very intimately connected to the issue of macroscopic quantum effects, which is quantum dissipation. And so I will talk about possible models and applications and practical results of quantum dissipation in some condensed matter systems. And in the third lecture, I will talk about experimental realizations, and I will address the issue of superconducting qubits. So the idea is the following. I will start with superconductivity, but I don't really want to bother about the microscopic theory of superconductivity, because to reach my goals, what I need is really some phenomenology of superconductivity, and that will be enough to describe the phenomenon I'm interested in. So to start with, let's briefly remember what superconductivity is all about. So what we have is that below a given temperature, many metals, they start to transport charge without any sort of measurable resistance. And on top of that, there is also the so-called Meissner effect, which is the complete expulsion of the magnetic flux inside this superconducting specimen. And so all these flux lines, they are expelled from this superconducting body. And so these are the two main features of superconductivity. And so how can we explain these sort of things? One very nice and simple is the pair of phenomenological London equations. And these two equations, they relate, for instance, the electric field to this sort of persistent superconducting density, current density. So in this sense, we can, if I have zero field, I can still have some sort of fixed persistent current. And the other one is that this persistent current in, for instance, the bulk superconductor, they can generate some sort of magnetic field. And that will be responsible for the expulsion of these lines of one external field that I impose to my superconducting specimen. And so I can combine, so these two are just constitutive relations. And I can use, for instance, I can combine the second one to the well-known Ampere law that I write as these Maxwell equations. And by just taking the rotational of this second equation here, I can get this equation for the magnetic field. And that also allows me to relate this penetration length to the London constant lambda. And that's the relationship between these two. And so with this equation, I can easily see what happens to the magnetic field. So in the normal region, the field is a constant. But then as I start to penetrate the superconductor region, what happens is that we have the reduction of the intensity of the magnetic field. And so that's the picture of what we have. So close to the surface of the superconducting body, we still have some penetration of the magnetic field, but it will take place only within this very, very tiny length called the London penetration band. And so as we start to increase the external field, we can destroy superconductivity if you reach some sort of critical field. And close to the critical temperature, this critical field will be zero. So that's the picture that we have for the penetration of flux in the superconducting volume. Now, if we have no scalar potential, scalar electric potential, we can say that these first London equations can be also connected to the expression for the electric field, which is minus 1 over c, and the partial derivative of the vector potential with respect to time. And using these two equations here, we can just say that the persistent current density will be equal to the vector potential minus a constant. And this A naught here is constant in time, but you can also study the form of this A naught. For instance, when we have quasi-stationary processes and things like that. So there are some sort of approximations we can use and try to simplify this expression here by studying what the sort of value this A naught would have. And we can choose, for instance, the London gauge, namely that we can show that under certain circumstances, this A naught can be given by the transverse component of the current density at the surface of the superconducting volume. And in this way, we can, since there is no flow of charge to the outside of this superconducting specimen, we can say that this A naught is zero. So we end up with this so-called London equation in the London gauge, namely that the superconducting current density, the persistent current density, is proportional to the A field. So that's the London equation. And so this is a very nice equation, and I'm going to investigate under what circumstances we can understand what is behind this equation here. The first one, we can use the famous Bloch theorem, not that one of the periodic potential, but another one which says that the ground state of a many electron system has always zero total momentum. And of course, it is valid also for the superconductor, since the superconductor is a ground state, a given ground state of one set of electrons, right? So it's an electronic system, and again, I can apply the same sort of theorem to any sort of electronic system, and interacting or not. And so the total P is zero. So let's think about a single particle. What happens then? So if I have a momentum of a particle subject to an external electromagnetic field, we can say that the total momentum is the mechanical momentum plus this field momentum. So if we also impose that the average of this mechanical momentum can support, for instance, these persistent currents, we can connect these two, the average value of the mechanical momentum to the persistent current. So we can say that by this theorem here, the average value of P is zero. So the average value of this mechanical momentum will be proportional to the A vector. So again, that's the London equation. So we are imposing that the mechanical momentum is fixed. So we have this sort of persistent mechanical momentum, and that is in agreement with the London equation. So in this case here, the London penetration depth will be given by this expression here. Now, so let's try to understand that in terms of quantum mechanics. So if I take only a single particle wave function for one particle, and I try to describe the charge current or charge current density when the system has this sort of has a wave function given by psi naught. So that's the well-known expression. I multiply the probability current density by the charge. And so that's what we have. E divided by m, the real part of this psi naught star p psi naught. And again, in this case here, so there is no external field. In this case here, we have Js given by 0, because the total momentum and the mechanical momentum are the same. But then if I apply an external field to my system, I change my wave function to psi. And I also have this term here, because I have to perform this sort of transformation here, that the mechanical momentum will be P minus this EA by C. So in this case here, that's the new form of the persistent current when I have an external field. And but now, if I assume that the wave function of my system is rigid, so it means that just applying the field, I will not change the structure of this wave function. So all I'm saying is that this new wave function will be the same as before. So the magnetic field, of course, if I put a very, very strong field, I can destroy it. But for moderate fields, what we have is that this wave function will not change. And then in this case here, what we can say is that psi naught is still the same as psi. And then, again, we are back to the Coulomb equation. So that's what we have, that these persistent current is proportional to the A field, and psi star psi, which is can be related to the number density of carriers. So that's again what happens. So in this case, we can say something about, without going deep into the microscopic details of the theory, we can say that there is some sort of gap in the spectrum of this electronic system, because the gap is there, so the wave function has a sort of gap. So I cannot destroy this gap for moderate fields. And so that's what's behind this assumption here. And now, I've been talking about the single particle wave functions, but we know that the many electron system has a many body wave function. So in general, let's say that my ground state is given by this function here of n variables. And if I have to cope with persistent currents, I must say that all these bunch of particles can move without resistance. And so we can have this sort of translation states. So I can move the whole set of electrons with a constant velocity. And in this case here, I can define this psi k. And of course, it differs from the previous one by this sort of phase factor here, that is saying that we have this big K as the wave vector for all these particles in the ground state of the superconductor. So we can also generalize that, because if we remember what happens within the superconductor, we must have some sort of current density close to the surface of the superconductor. So this current density must be position dependent. If it is position dependent, I can try to generalize this sort of thing here, right? That is appropriate for the uniform motion of the whole set of electrons to this new phase. And this one here will contemplate this possibility of having this position dependent current density. And so with that, we can compute the average density of particles, which is given by the average with this wave function here, or this wave function here, right? And the current density, which is given by this expression applied to the delta function, and the delta function comes from this formal expression here. So we can have this carriers density or the current density given by these two simple equations which are related to this wave function there. Of course, psi star and psi will always cancel this phase here. And then, using that sort of expression, we can say that our current density will be given by EH bar by M, charge density, and the gradient of the phase, right? So that's the sort of expression that we have here. And the phase now written as a function of a single variable, right? Because I have already traced many of these, integrated many of these degrees of freedom. And the density is given by this n times the integration over n minus 1 particle, because there is that delta function there, and the delta function will always filter one particle, and then you can integrate over n minus 1. And so that's the sort of expression that we have for this density. Now, let us assume that the ground state is a non-interacting ground state, like in a BC, for instance. In this case, what you can say is that this wave function here will be the product of non-interacting wave functions, and then I can integrate n minus 1. And in the end, what we have is that the density is n times the probability density. Now I can also say, okay, fine, I can change the normalization of my wave function and jump to this sort of what people call the superfluid or superconducting wave function, which is square root of n and the exponential of I theta. But now, listen, that's a sort of a pure state, right, that I'm playing with. And on the other hand, we have that phenomenological information tells me that, phenomenology tells me that the two-fluid model is something important. So we always have the persistent current and also normal current in our material. So we have this coexistence of two fluids, a superconducting fluid and a normal fluid. So normal electrons and superconducting electrons. So, so in this case, this sort of behavior, this sort of description is not very appropriate. So what we should do instead is to think about the reduced density operator of one particle, and in the case of zero temperature is given by this expression here. I just pick one of them, and that's the diagonal element of my one particle operator, reduced density operator. So, and in this case, of course, any one body operator like the full kinetic energy of the system can be written in terms of the average of this reduced density operator. And with that, of course, we can always relate this reduced density operator to the description of wave functions. But we must be very careful with that. We can also jump instead of, because as I said in the beginning, I'm not going to address the issue of the microscopic theory of superconductivity, but we know that the superconducting carriers are Cooper pairs, and all this knowledge we already have. And so it's important to think about the reduced density operator for two particles. And in this way, I take these again for zero temperature. Otherwise, I have to modify the description and think about averaging over many possible wave functions with given probabilities. And but for zero temperature, that's this expression we have. And so we can play with two body operators like the interaction energy between these particles. And that's the sort of average that we have when we play with this reduced density operator of two particles in my system. So again, if I think that my particles in the condensate, they are just non-interacting particles that must be anti-symmetrized because they are fermions, for instance, I can write my reduced density operator of two particles as n minus 1, and the product of these two body wave functions. just simply two body wave functions. And now I can jump for to the center of mass and relative coordinates of this guy here. And so in this way, that's the way you can write the reduced density operator of one particle. And if I assume translation invariance, the center of mass and the relative coordinates can be decoupled. And then we're back to the description of a single particle wave function. But now I'm referring to the center of mass of the pair, right? So again, we're back to the square root of n e to the I theta as the wave function, single particle wave function description. Again, we have to be very careful because of the two-fluid model, because the right prescription will be really to address the question of the reduced density operator for one and two particles. And then we can relate that to the off-diagonal long-range order and to the order parameter in Ginzburg-Landau sort of approach. So, but again, to our present purposes, all we need is this sort of description here, description of the single particle wave function for the superconductor. Now, so let me address two nice and very important effects. The first one is the flux quantization. If I just apply that expression that P is equal to the canonical momentum plus EA divided by C, we apply that to the single particle wave function, and then we end up with something which is the gradient of the phase. The gradient of the phase is equal to the mechanical momentum plus this field momentum. And if I integrate that along a path, that's the result. So that's the difference of the phase of the wave function, and that's the integration of mechanical momentum and field momentum. And then if we have a simply connected region, of course, you know, if I close any sort of circuit, my difference of phase here will be zero, and there is no current, there is nothing there. It's a trivial result. But then if we have a hole with a magnetic field, and we can encircle this sort of hole in this, by this integration path, and I can connect this mechanical momentum to C London constant J, and that must be the difference of the phase of a wave function going from one point and coming back to the same point. And the difference here is 2n pi. And so what we have is that deep in the superconducting ring, there is no sort of current here, right? And so what we have is, all we have is the line integration of the vector potential. And that turns out to be the flux, because that's the surface integral of HDS. And so in this case here, this integral of J is zero because I'm deep into the superconducting region. So all this persistent current, it will be flowing by the surface, right? And so in this case here, what we have is that this line integral of A along this line will give us n phi naught. And this 2e here, usually what people write is ES. So that's the superconducting charge, right? That's the charge of the superconducting particle, the superconducting carrier. And in this case, by the experimental results, this charge is 2e. So that's a sort of experimental input that we need. And then we can say that the flux inside this ring is n phi naught. And phi naught is the and it's HC divided by 2e. So that's the first nice effect I wanted to tell you about. And now what we can do is to jump to the second one, which is the Josephson effect. The Josephson effect is we have a junction and two superconducting regions connected by a point contact, a sort of a tunneling barrier, whatever. And then we have this sort of description for the wave function. K is 1 or 2, right or left side. And then I can write this, I can deduce that by this simple approach given by Feynman, which is that's the wave that the Schrödinger equation for the wave function of the superconductor on side 1, and it has the influence of the wave function on side 2. And for side 2, I can write a sort of wave function for side 2 under the influence of the overlap of the wave function of side 1. So we can easily solve that. Actually, we can apply this sort of equation for this description here, and then we end up with these couple of equations. One, the same for the superconducting 2, and these two here, and this second equation is the same for both 1 and 2 cases. And then what we can show here, for instance, is that these two equations can be written in a different way here, which is that I is I naught sine of delta theta. And delta theta is just the phase difference between these 2 points here. And the phase difference, the time derivative of the phase difference, is given by the potential to which the junction is subject. So what we can say is that if there is no potential difference, the phase difference is constant. And if the phase difference is constant, we can have a flow of charge from one side of the junction to the other. And then when we have that, that's what the Josephson effect is all about, is the transport of charge through this junction without no sort of voltage connected to these 2 points. Now, I will try to put these two effects together and try to make the to study what happens to the line integral now of the momentum once we have a junction here. And so in this case, it goes exactly as before, with the only difference is now that I have to account for the jump here, because I'm not really coming from 2 to 1. So there is this vacant region there. And so I can say that the full integral over this path gamma from 1 to 2 is just the closed integral minus the integral from the gradient of the phase from 1 to 2. And that turns out to be, so this integral will be 2 pi n, because this one is the closed one, minus the phase difference. So in this case here, instead of phi n phi naught, we have this extra bit here that has to do with the phase difference across this point contact. And the total flux is given by the external flux plus the self-inductance and the total current. So the total current is, of course, the Josephson current through the link, and a normal current, which is the difference of the potential difference divided by the resistance of this point contact, and the polarization current, which is CV dot. If I add these 3 contributions here, and use that V is equal to minus phi naught, so this change of the flux through the ring, we can write the full equation, the dynamical equation for the flux inside the ring in this way here. So we can say that these dynamics of the flux inside the ring is given by one sort of inertial term, a dissipative term, and a term which is the derivative of an electromagnetic potential energy, which is given by this expression here. So this phi x is the external magnetic field times the area of the ring. So I can control that. So I can control that thing. So I can control the form of this electromagnetic potential energy. And depending on this choice here of parameters, L, the critical current, and phi naught, this U of phi, namely this function here, has either several minima or only one minimum. And so these are the possibilities. We have a sort of parabolic term and the cosine term for the electromagnetic potential energy. So if I change the external flux, I can create what was a sort of a zero current state, zero flux. It's very close to zero, but now it has another sort of configuration of currents that have a finite flux with the same energy. And the third one, I can bias this external field with the quantum flux. And in this way, I transform my stable initial state into a metastable state. And the next state here is the stable one. So I have a stable configuration, a bistable configuration, and a metastable configuration. Now, if I put numbers in this squid, for instance, these squids can be very, very tiny. These are microscopic or even nanoscopic devices. We can have 10 to the minus 10th Henry and capacitance of 1 picofarad, and the critical current can be minus 10 to the minus 50 ampere. And so in this case, omega square, which is 1 divided by LC, something order of 10 to the 22nd. And in this case, if I estimate the temperature, H bar omega divided by KB, it is less than 1 degree, 1 Kelvin, sorry, 1 Kelvin. And so in this case, we're talking about easily attainable quantum mechanical regime, right? And for temperatures below 1 Kelvin, we are already in the quantum mechanical regime. So that will be a quantum effect of this electromagnetic field, because we're talking about flux. And so we can think of these squids as giant atoms or molecules, where you can study the energy level structure of this guy here, energy levels. We can study decay of this metastable configuration going to the other side, or oscillations between these two stable minima. Well, but then there is one question. What is really tunneling? We are boldly talking about the quantum mechanics of the flux, as the flux were a sort of a coordinate of a particle. And what's the real meaning of these quantum mechanics we're talking about? Now, what you can say is that we have lines of these flux lines inside the superconducting ring. And now, if I take, for instance, the bistable potential, so there is one value of flux going to the other value of flux. So what we have is some sort of fluxoid tunneling. So if I had the extreme case of very huge barriers between these two minima, I will go back to the case of a uniformly closed ring. So they will be quantized. But now, there is a possibility of transition from one quantum of flux to the other value of quantized flux. Now, I can also go back to the case of the Josephson junction, but now all I'm going to do is to get this sort of expression from the behavior of the squid. If I relate the flux to the phase difference and take a huge squid and with infinite external flux, because the area is now infinite, but in such a way that phi x divided by L is given by the bias current. But we have, instead of these parabolic plus cosine potential. What we have is the so-called washboard potential, and the equation of motion for the this variable phi, which is related to the phase difference of the wave function, is something given by this equation here, exactly like before. And that's the Josephson coupling energy, phi naught, I naught divided by 2 pi. And so that's the picture. What we have here is the washboard potential, is a potential like that. And we can tunnel from the state of, so I can start to tilt this potential and wait for some time in this minimum here, and then I'll start to develop some sort of phi dot. So I'll jump for this sort of running state, which has some dissipation, which has some sort of finite voltage. And so as I try to convince you that this quantum mechanics I was talking about had to do with the flux going from one side to the other. And we can also investigate the quantum mechanics of the Josephson junction, just the tunneling of one phase state to the other along the same lines. The only difference, we have to think about a fluxoid going from one side of the junction to the other. And every time, for instance, if I take the line integral of this fluxoid going from one side to the other, we can always claim that there is a phase difference going from the upper path and the phase difference going to the lower path. And if I take the difference of the two is 2 pi, because that's the phase difference of the fluxoid going through, so it's a 2 pi, the line integration would be around the circuit. And so if n vortices cross the junction, we can say that this d delta theta dt is 2 pi in the n dt. And so I can understand the voltage, which is related to this time derivative of the phase difference in terms of this transport of lines across the junction. So, in this sense, well, I can say that I tilt this potential, and then I have the possibility of lines going from one side to the other, and that increases the current. So that's why we can have something like this. So I go to the other side, and then I will run downhill. And but then we can say the same in this case here. But now there is a transmission of the crossing of one of these lines going to the other side, generating current. And after that, there is a sort of avalanche of many of those going to the other side. So that's the running state. So that's a way to see that. But where is quantum mechanics there? Well, quantum mechanics is exactly when the first one crosses the junction, right? And then what you can say is that we have flux lines here, flux lines there going into the slide, the other one coming out of the slide. And there are these arrows, they represent the intensity of the current. Now, what happens is that we have, okay, that's the picture that we have, but now we translate it. So let me go back. So that was the initial state. Now, what happens is that I can just tunnel one line from one side to the other. So I'll increase the number of lines going into the slide, and those coming out from the slide, and I can create more current too. So that's the picture that we have, and that is a sort of quantum phase slip. Now, we were talking about this washboard potential, with this periodic potential. And I was thinking about the phase phi as a coordinate of this potential. But that depends, the question is that the most appropriate description for my system? And the answer is, just inspired in the same example in solid state physics, periodic potentials, we can either play with the picture in coordinate space or momentum space, depending on these energies here. The tight binding model is very appropriate for this sort of a hopping description and the tunneling from one side to the other. But if we have a very strong charging energy, that's much more appropriate for the nearly free electron model, that we just disturb the free electron model by a periodic potential. And when we do that, we can use the Bloch approach, this problem, and instead of treating the problem the same way I've done before, what we can do now is to remember that charge now is minus IH bar and the derivative with respect to this variable here, phi naught, phi divided by 2 pi. So this guy here plays the role of position, and this guy plays the role of momentum. And now I can, by Bloch theorem, we have this sort of function here, where the charge divided by 2e plays the role of the wave momentum. And this function u is 2 pi periodic. So what we can have is that instead of feeding a current, we can feed charge very slowly into the system by a gate voltage, for instance. And now, so that's in the end, adiabatic approximation, that's the new Hamiltonian that we have. And so that's more appropriate to look at the system in the K description, the wave vector description. So now we're thinking about changing the charge. So we can change the charge, and that's the number of Cooper pairs, 0 Cooper pair, 1 Cooper pair. And as we turn it, we can make some sort of Bloch oscillations, or we can Zener tunneling for the next band. The Zener tunneling here is something very close to the running state, because then if I just cross this gap here, I will just run downhill, because the other gaps will be very, very, very tight. So now I want to address, so I talked about these two devices, and now I want to say something about vortices in superconducting materials, superconducting bulk. So what happens here is that what I mentioned so far was the type 1 superconductor, that I can put some sort of external field, a very strong field that can destroy superconductivity. But usually what happens is that first we penetrate the specimen with many flux tubes. And only when I reach the second external field, I fully destroy superconductivity. So the first phase between HC1 and HC2 is the so-called vortex state, where I have all these vortex lines penetrating the, say, a cylinder. I have all these flux lines penetrating the cylinder, and that's the these Abrikosov vortex state. Now, the important thing here is that there is a new, instead of only that lambda that has to do with the penetration of the field, what we have now is second length, which is the basically the coherence length of the Cooper pair. And we can estimate that just by remembering that there must be a gap in the spectrum of these superconducting material. And so that's what happens to the momentum, P squared, the kinetic energy, is just between EF plus delta, EF minus delta, and then we can estimate the uncertainty of the momentum of electrons close to the Fermi surface, and that's the value. And then we can use the uncertainty principle, and we can estimate the size of the Cooper pair. And that's basically H bar by delta P, and that's the value that we have. From the microscopic theory, you must replace this 2 by pi. And so that's the coherence length. And then we have the competition between these two things, the coherence length and the penetration depth. And depending on the, when lambda is very small and the coherence length is very large, we have the type 1 superconductors. Otherwise, we have these these vortices penetrating as very tiny filaments. And in this case, you have the type 2 superconductors. So these are the appropriate ones for the London theory. And so what we have here is to average. For the type 1, we have to average over A. J and A, they are not only proportional, but there is a theory by people, but that's beyond the scope of my talk. And so we can also play with these surfaces within the superconductor and try to see when we have the vortex penetration or not. And so if you have an abrupt penetration of the field, that's what happens. The normal free energy density minus the superconducting free energy density is given by h squared by the critical field squared divided by 8 pi. And now, when we have this competition between these two lengths, what happens is that there is this change of the free energy difference. And then in this case, we can show that for type 2 superconductors, when lambda is much greater than psi, we want as many vortices as possible. But then we have to also to think about vortex-vortex interaction. And then in this case, we can end up with this sort of stabilized hexagonal lattice. So they will not simply expand, right? So by then we have this Abrikosov lattice. Now, we can now play with the density. What happens to these vortices within the superconducting specimen? We can play with the energy density, the linear energy density, and that's given by this expression here. H squared divided by 8 pi is the density of electromagnetic energy stored in this sort of region. And the rotational of H is just the current, H proportional to the current. And now we can play with this guy here. And we can say, for instance, that we can distort this line, right, about the one equilibrium configuration. We can distort this line and we can compute all these possible energies associated to the line. One of them is the elastic distortion of the vortex. The second one has to do with the mass, because within the vortex, what we have is a normal region. And in this normal region, of course, we destroy this gap. And then we have these electrons now within this finite region with strong potential. And now we can estimate what happens. What is the sort of linear mass density of the vortex line? And then I can just play with these, the Fermi energy density, electronic density, and delta E that I told you about. And so that's the value of this fraction of electrons per unit length within the flux tube. Now, just playing a bit with these values, we can say that the linear density of mass for the vortex tube is something like the electronic mass times the kf, which is the Fermi wave vector. Okay, now, what are the forces on I'm talking about a single line, right? I'm just analyzing what happens to a single line. And then we can, thinking about these, the electromagnetic behavior of this line, and we can show that there is a sort of Lorentz force acting on each of these tubes. And that has to do with the superconducting current times the phi naught. So phi naught is the quantum of flux along the z direction, for instance. And there is also the Magnus force related to the, there is the superfluid flow and also the motion of the vortex relative to the superfluid flow. And so that's the expression here. If we take these a stiff vortex, we can study, for instance, the dynamics of this vortex. And I'm also, all I'm doing now is to introduce two other terms. One is due to dissipation of the motion of the vortex line. And the second one has to do with the Hall effect. And playing with these two guys here, we can show that there are two terms proportional to the velocity in the equation of motion. And these two terms, one of them is related to dissipation and the other one related to the Hall effect. Usually, we're talking about omega naught tau, very, very small, going to zero. So in this case, this term here is omega squared, tau squared. So the dissipative term will dominate the motion of the vortex line. Now, so we can also think about pinning of these lines here. So due to impurities and many other things, we can pin these vortex lines. And so in this case, we can have a very general equation for the displacement of these vortex tubes, right? And so that's the inertial displacement, and dissipation, that's the whole term. That's the elastic contribution and the pinning. So it's like an elastic line on the sort of on a potential, right? Like the roof of a house. And so that's what it is. That's the elastic line. So that's the picture that we have. And the line can go from one minimum to the other. So we have something like nucleation processes. From part of the line, we'll hop from one minimum to the other, and then we can transform the whole system into a more stable situation. Now, okay, so let's come to the last part of the talk. I have been describing systems and talking about possible quantum effects of collective variables. And these collective variables, they, of course, the underlying physics has to do with the microscopic components that we have. But the thing is, what is really happening? Why are we calling that macroscopic quantum effects? And I have tried to address that in terms of flux. Flux lines, just fluxoids going from the inside to the outside of the ring, or quantum phase slips, or I can think about the quantum mechanics of small, tiny pieces of a vortex line. But still, these are nice because I can understand what happens in terms of the quantity responsible for these effective dynamics. But now let's try to have a look at the electronic system. What goes on in this electronic system? And so for the squid, let's address the question with the squid. For the squid, we had one quantum state of the electromagnetic field and the quantum state of matter, namely superconducting electrons. And there is another stable configuration, which is the final one. Well, let's take the metastable configuration. So we have the stable one and the metastable one and the stable one. So I can go to the final state, which is a different electromagnetic state and a different electronic state, because now I have a different current state. So we can make this sort of course, you know, I'm not being very rigorous here, but we can understand that like the total wave function will be something like the initial configuration of the electromagnetic field, the initial configuration of electrons, and the final configuration of the electromagnetic field and the final electrons. And of course, I'm just saying that once this metastable decays, it will never come back. So that's a sort of a hand-waving attitude, right? And so that's the sort of state that we have in the end of the day, right? So I started the metastable state, and then I end up with something which is stable. But more interesting than that is the bistable configuration. Because in the bistable configuration, I have one initial configuration for the electromagnetic field, namely the flux, and the other one for the electrons. And the same for the final state. But the thing here is that, so what do we have? If we can really make sure that the line is coming from the inside to the outside, back to the inside, back to the outside, we have a sort of coherent oscillation. And this coherent oscillation, it has to do with this sort of superposition here of states here. And the superposition states, these are Schrödinger-like cat states, right? Because, you know, it has to do with the linear superposition of the full condensate going in one direction or the other direction. So when we talk about that, we're really talking about, if I stop thinking about the flux state and look at the electronics of the system, what is happening? What happens is that we either have the current circulating this way or the other way, and we have genuine superposition of these events. What about the Josephson effect itself? The Josephson effect only, the one that we have the overlap of the wave function on one side of the junction to the other, is not exactly the same sort of state. Because in order to describe that, what we need is just a linear superposition of pair states on one side and pair states on the other side, and then make the product of these functions. But the product, you know, is not a big deal. The big deal is in here, is the linear superposition. And the linear superposition as in here, because now we're really talking about a huge number of particles in one state of motion and the other. And whereas here, downstairs, what we have is different. It's not the same. And what we have is this sort of linear superposition. Pair, okay, this already has something, you know, a pair tunneling from one side to the other, but still, it's not exactly the same state as this one here. So I would say that's a sort of maximally entangled state in the language of entanglement and something more fashionable. So that's a sort of Josephson-like wave function. And so let me say a bit. I talked about this phase slip representation for the Josephson effect. Then we could think of a quantum phase slip, line crossing from one side to the other, right? But that was a flux description. Again, now what I want is a sort of electronic description of this effect. Now, we can jump again for our description of the very tiny Josephson junction, where I have a very high capacity of energy, because C is very small. And then, in this sort of equivalent mechanical model, I will say that I have the quasi-free electron model. And then, as I showed you before, now we can describe the physics of the system in terms of K, namely the charge. So I'm feeding charge to the system. And then we can feed charge. Then I reach this level crossing. So this is a state with 0 Cooper pair, right? Excess, right? And this state is 1 Cooper pair excess. So what I'm doing is to feed charge to one side of this capacitor. The other side will have minus E. So in terms of charge configuration, this picture and this picture is absolutely the same, right? And so what I have is a charge E on the left and minus E on the right. So that's what it is. Now, what we can do, and that's completely indistinguishable from the this former charge configuration, is the one that I feed E minus E to the other side, and now I tunnel one pair. So one pair will come from this side to this side here, or the other way around. So in the end of the day, what we have is a charge state exactly like this one here. But now I have moved one pair to the other side, and that causes some sort of Josephson coupling energy. And that's why when we have the superposition of 0 and 1 Cooper pair, we have this the opening of this gap, right? So so that's what we have in the end of the day, right? We have either we can tunnel the Cooper pair from one side to the other, and then we have, if we could just take one Cooper pair to the other side, pay no Josephson coupling energy, these guys will be in this point here. But now what we have is that there is this sort of coherence oscillation from one Cooper pair from one side to the other, and not the avalanche. So that's the thing here. The avalanche means that this guy here will cross the other side, and then there's a sort of Zener tunneling, and then it will go, right? But not now. Here is something more related to a sort of Bloch oscillation, right, within the lowest band. Okay, so so that's the picture that we have. So I try to show you that these devices, either superconducting devices or vortices in a superconducting bulk, these guys can behave quantum mechanically. If we look at the electromagnetic field configuration, it's more or less reasonable to understand what's going on in terms of fluxoids going from one side to the other, things like that. But the nice issue here is to look at the electronic part of the system. How is it behaving? How is it responding for this sort of physics of the electromagnetic flux? So looking at that, we say that finally we can have all this picture, which is quite funny. We can have something like Schrödinger-Cathy state, or something like just the superposition of Cooper pairs from one side of a box to the other. Then, in this way, we are on safer grounds. If you want to just say the phenomenological equations of motion for these effective variables, flux, phase difference, they do make sense. Because now what we have to do, we know what's happening underneath. We know exactly how the microscopic degrees of freedom of electrons, they are responding to that. So I can go back to my original equations and try to make the quantum mechanics of all of them with no problem, because now I know the interpretation of what is going on. And moreover, I have something new to think about, because in all those equations, we are always thinking about dissipation for squids, for the washboard potential, namely Josephson junctions, and for the vortices. In the bulk superconductor, we always have something like this. And the issue here is to reconcile, these ideas of quantum mechanics and dissipation, and that's the subject of my lecture tomorrow, which is the that will address the issue of dissipative quantum systems. Thank you very much.
Thank you for the lecture, Professor Caldeira. We are a little bit short in time, but I think you have time for 1 or 2 questions from the audience. Please. Okay, you can come.
Hi, thank you for the talk. So my question is, given that you have quantum vortices in the system, can you have a system with a lot of quantum vortices that interact with themselves and have like a quantum turbulence regime in a superconductor?
Sorry, can you repeat the question, please?
Yes, can you have a system with several vortices, quantum vortices in a superconductor that interact between themselves, reproducing like a quantum turbulence system?
Okay, of course, we can think about the vortex interaction. Actually, that's the interaction responsible for the creation of the hexagonal lattice, the Abrikosov lattice. So, you can think of the effects of quantum turbulence, but it is not in terms of interpretation of what is going on. Because for all these examples I've just given, we can trace a parallel with the BEC systems, and you can try to understand the same sort of things. But the problem now is when we talk about this multi-vortex state, everything I'm doing here, even if I'm going to address, for instance, magnetization, relaxation of a superconducting cylinder, if I change the external field, of course I will address the issue of the transition of many of these vortices from one stable configuration to the other. But then I will always neglect self-interaction between them. I never really thought about quantum turbulence and how you would apply these methods. Well, even classical turbulence is so complicated, I don't really know. But the only one thing I can tell you is that the ideas that you can try to extend to quantum turbulence and this dealing with self-interaction between the vortices, of course they will always rely on something simpler, namely what happens to a single vortex. And so that's all I can say. I never really thought about the problem of quantum turbulence.
Okay, thank you. And experimentally, can you observe and study the dynamics of these vortices?
I will address this question in my last lecture, right? Then I will show you many experimental evidences of the of tunneling, of coherent tunneling, and things like that, and the effect of dissipation on these quantum mechanical phenomena.
Okay, thank you.
Thank you. Thank you, Professor Caldeira. You're running in time, so we have to move for the next lecture. And I'd like to thank you and see you tomorrow. Okay?
Thank you. Bye.
Okay, bye-bye.
Our next speaker is Professor Tommaso Macrì from Federal University of Rio Grande do Norte. Tommaso comes from Italy, where he got his PhD. He worked in the Max Planck Institute for Complex Systems and also the Max Planck Institute for Quantum Optics. And since 2015, he is a professor in Natal. He has been working with the physics of cold atoms and will speak to us now. Is Tommaso online? Okay. They're telling me to wait. Okay.
Você falar, põe mais perto. As we prepare, Tommaso lives in Brazil, he's Italian, and he's in other place. I don't know where he is, but he's somewhere. He's in Boston. Okay. Well, as they prepare, let me tell you that the dinner, let's try to go to the dinner around 7, because the restaurant is open at night mostly for us. So I know that some people want to escape once in a while, go for a little bar. It's okay. But the people that should go like, 7 o'clock. Then you can rest, have fun, or do anything you want, okay? Let's try to go around 7. Otherwise, they stay open waiting, because we gave a list. And we said, well, if nobody shows up until 8 o'clock, you can close down. Is that fine to everybody? Yeah. Should not eat it too late, huh? It's no good. So try to have a good meal early. Thank you. Okay, this is Tommaso.
Hey.
Okay, Tommaso,
Manuel.
we presented you already, so please just start. Welcome.
Okay, Manuel and Vanderlei, thanks a lot. So I was actually seeing you, but I couldn't listen the introduction, unfortunately. But nevertheless, thank you very much, first of all, for inviting me and for the opportunity of being here with you, although only virtually. It would really been a pleasure to stay with you guys there in São Carlos. I'm not in Brazil right now, I'm in the US, so for this reason I couldn't be physically there with you. Okay, before starting, I want to anticipate that the lecture of today probably will be slightly shorter than the next two, so just for you to stay also on time for your lunch. The topics that I will be covering will be essentially focusing on two big top or subtopics related to quantum simulation and long-range interaction. So quantum simulation is essentially a sub-area of a larger field, which is the one of quantum technology. And I will be focusing on this essentially during the lecture of today. It will be very introductory, so mainly for grad students, essentially. And then in the next two, I will be talking about platforms that display long-range interactions and also present some applications. What I will be discussing with you, of course, I will make it available both online. If you're interested, I can also share additional information at any moment. Don't be shy, so just ask questions either now or at any moment. You can drop me an email. We can also chat on Zoom if you wish. I know that many people are also attending the event online, so again, guys, I'm available. So let me also thank the funding from SPSAS, CAPES, and EPQ, and the support from the Federal University of Rio Grande do Norte. So before starting with physics, let me first advertise the place where we work. So we are based in Natal, which is located in the northeast of Brazil, really at the tip of the South American continent. And this is essentially a postcard of the neighborhood of Ponta Negra, which is a very touristic place, and the university is located just a couple of kilometers far from this nice resort. And this is our group. At the moment, we have three postdocs, Arsenio, Flavio, and Vinicius. Arsenio and Vinicius are attending the event online, probably I don't know, probably they interacted with you or either via Zoom for their poster session or to ask questions. But again, ask them if you have any question which is related or unrelated to the topics that I will be presenting. We have 4 PhDs, Igor, Heitor, Santiago, and Lucas. Igor and Heitor are here in the pictures. Heitor and Santiago are there in São Carlos physically. So again, just talk to them, try to ask questions, interact with them. They are very happy to discuss about the research that they've been doing. And finally, we have 2 undergraduates, Arturo and Caio. So our research is essentially focused on different aspects of quantum simulation that are essentially related to the physics of ultra-cold atoms, but they apply to a broader set of research areas such as condensed matter, AMO physics, or even quantum sensing and metrology. So in particular, Arsenio and Vinicius work more in the area of strongly interacting many-body systems, also with advanced numerical methods. And Heitor works on nonlinear optics. And then we have we will have another talk in the next few days by Thereza Paiva, who will be talking about recent work done in the field of quantum coherence for applications to metrology and strongly interacting many-body systems. Okay, so now let's move a little bit to the physics and try to motivate the content of the first part of the lecture. So quantum technology is essentially very much related to what is nowadays called the second quantum revolution. The first quantum revolution actually started almost 100 years ago when we started to understand, to propose the laws of quantum mechanics, understand them from the microscopic to macroscopic level. Instead, more recently, I would say over the past 20 to 30 years, we tried to put some effort also to apply those concepts, really using them for a set of, to solve a set of tasks, essentially, with different types of platforms, namely photons, electrons, atoms, and molecules. So these are essentially the tools. And the areas of applications are related, are called, let me just, sorry, I have a problem here with my Zoom. Okay, with my video. Okay, now I solved it. Now the applications are related, that can be subdivided in 4 big areas that are defined as quantum communication, quantum computing, quantum simulation that I will be focusing on over the next hour or so, and finally quantum sensing and metrology. And all of these areas, of course, are based on strong foundations given by the work that we do every day, which is essentially basic science. The information that I'm presenting to you is contained in a document which is called the Strategic Research Agenda of the European Union, but you can find a really similar type of information also for the Strategic Quantum Initiative by the US government, or more recently by the Quantum Information Technology white paper that was recently put forward by the government, by actually researchers in the state of São Paulo, where they currently are. So this is sort of very broad overview. I will be, of course, focusing on quantum simulation, but before that, let me just give a brief overview also of the other fields. So by quantum communication, basically we mean essentially the generation and use of quantum states and resources for communication protocols. And the key word here in this field is essentially quantum cryptography or quantum security associated to that. And the tools are quantum networks and repeaters. Quantum computation, broadly speaking, has to do with the development of the quantum computer, which is essentially a device that harnesses the laws of quantum mechanics to solve tasks in a more efficient way than classical computers. And this can be done essentially with a variety of platforms, and also by implementing advanced quantum algorithms that can work on quantum computers. Quantum simulation instead has to do with the highly controllability of certain types of quantum devices that essentially allow us to obtain insights into the properties of complex quantum systems to solve computational problems that are essentially inaccessible to classical computers. And as you can understand, there is a really huge overlap with the field of quantum computation that I was mentioning in the previous slide. Quantum sensing and metrology instead has to do with basically with exploiting the laws of quantum mechanics to perform certain tasks such as sensing certain types of electric and magnetic fields, gravitational fields, or by reducing the certainty of atomic clocks by performing again tasks that are not available, or by essentially using techniques or essentially properties of quantum mechanics, such as entanglement, to boost the sensitivity of such devices. As I said, I don't want to enter into the details, but of course, if you're interested, I have additional material, and I will be happy to share it with you. Okay, so now all these things that I was discussing with you has really showed sort of an exponential increase of interest and investments over the past few years. These are some data that I took from the EU strategic agenda published in 2020. And as you can see, the number of patent applications really increased by a lot over the past 5 to 10 years. And the major players, as you can see, are essentially China, the United States, but there is also a relevant contribution by European countries and some other Eastern countries. Of course, this is not all the work of single independent individuals or countries, but there is a lot of interaction between them. You can see that there are actually many international collaborations between those entities. And the amount of investment associated to quantum technology is really huge. Even though we are still in the middle, I would say, of the pandemic, there are really tens of billions of dollars that were invested last year over the world, in the whole world, basically to boost the development of those quantum technologies. Okay, now let's focus a little bit more on the topic of this first lecture, which is associated to quantum simulation. Now, the whole idea of quantum simulation started with a groundbreaking paper by Richard Feynman, which is entitled "Simulating Physics with Computers." And essentially, this basically the main content of this paper can be summarized by asking essentially the right question at the right time. So what kind of computer are we going to use to simulate physics? So computer physics has been developed to a point where it realizes that it doesn't make any difference. When you get to a universal computer, it doesn't matter how it is manufactured, how it's actually made. Therefore, my question is, can physics be simulated by a universal computer? Now, the question is, of course, what type of challenges, what type of problems did Feynman envision and wanted to solve more specifically? So the problem that actually every one of us who do basically quantum physics at the many body levels, so when we really want to address several components that are interconnected, is essentially the fact that we have to deal with the exponential number of degrees of freedom as soon as we add additional particles or spins. This is the first question, so this is the first problem. But then once we store essentially the information of our state into our machine, then we want to operate on that. So we want to, for example, to perform some sort of evolution that also requires an exponential number of operations. So the recipe that basically Feynman proposed was essentially let the computer itself be built of quantum mechanical elements which obey quantum mechanical laws. Now the question is, how do we create a specific recipe for such a computer? Let me also mention that much of the information that I will be showing you today is based on already a slightly outdated review by Georgescu, Nori, and others, which is actually still very popular. It's a review, Modern Physics of 2014, but there are actually two more references which are much more recent that you can have a look. And I really strongly recommend you to do so if you really want to have a sort of big, large overview of the field. Now the question, the answer, a partial answer to Feynman's question was discussed by Seth Lloyd back in 1996, who proposed the idea of what are nowadays called universal quantum simulators, which is actually very much related to the idea of a quantum computer. Indeed, what is it? This is a universal quantum simulator. So it's an ensemble of well-defined qubits that can initialize the measured and on which universal quantum gates can be performed. It can act as a universal quantum simulator, and universal refers to the fact that, except for changes in the programs that it runs, the same machine is capable of tackling vastly different problems. Now, is this sort of question a little bit too ambitious? So, in some sense, it is, because do we always need a quantum computer to solve quantum tasks? The answer is actually no. Sorry. Sometimes, indeed, we can focus on a restricted class of simpler quantum devices which tackle specific problems. And this is usually what we do, for example, in the field of ultra-cold atoms. If you think a little bit, I will provide an example to you in a moment. So let's state a little bit more quantitatively the type of problem that we need to solve. So essentially, in quantum mechanics, we need to first define the initial state of our quantum system, and then we want to obtain the state of the same system at time t by applying a unitary operator, which can be written as the exponential of minus I ht over h bar. So this h bar is actually in the numerator, it should be in the denominator, not in the numerator, which is equivalent to solving the so-called Schrödinger equation associated to this Hamiltonian h. And for simplicity, I'm not considering the time-dependent Hamiltonians, but it can be straightforwardly generalized. So how do we solve it numerically? Well, it is first necessary to discretize the problem such that it can be encoded in a computer memory. So how much sort of memory do we need? So for n spins, we need 2 to the n complex amplitudes to describe the wave function. And then in principle, to compute the time evolution, we need to exponentiate a 2n by 2n matrix, which is to n. So for n equal 40 qubits or spins, we have something like 10 to 12 numbers for the wave function. So assuming a single precision, this amounts to around 10 to 13 bits, which is 4 terabytes, just to store the state of a 40 spin system. Now, how does this number scales? Just to have a sort of an overview of what 4 terabyte would translate instead for the case of 80 qubits. Well, you immediately see that is a sort of impossible task, because it would require just 10 to the 12 terabytes to store the wave function of 80 qubits. And just to make a comparison, to understand the orders of magnitude that we need to deal with when we talk about 10 to the 12 terabytes, so it is estimated that the Library of US Congress can be contained in 160 terabytes, and the amount of information produced by the humankind by year 2007 is of the order of 10 to the 8 terabytes. So here we are already 4 orders of magnitude larger just to store the state of an 80 qubit system. So it's really a sort of an impossible task. Now, let me try to be a little bit more specific. So quantum simulation nowadays is a very broad research area, and it can be sort of divided in three big categories. The first one is the so-called digital quantum simulation. The second one is the analog quantum simulation. And the third one is related to the development of classical algorithms that are inspired by quantum information, okay, or quantum information techniques. And I will provide an example for each one of the three categories. So, broadly speaking, the problem of quantum simulating a certain system that we want to understand in terms of another system that we will call the quantum simulator can be encoded, can be represented graphically by this picture. So suppose that we want to first define our initial state of phi 0 of the quantum system under study. This can be mapped into the initial state of the quantum simulator. This step is called the preparation of the initial state. And then ideally we would like to, by propagating the state of the quantum system with an operator, unitary operator U, find the properties of the final state. So this can be done by letting the initial state of the quantum simulator evolve with the different, in principle, different unitary operator U prime that evolves the initial state into the final state at psi of t, on which we will operate by doing some measurements. And therefore, by mapping back this final state into the state of the quantum system, we can get some results regarding the initial quantum system. So, of course, I understand this is sort of very broad statement. We need to be a little bit more specific. So, suppose that we want to study a magnetic system. So, in a magnetic system represented by a set of spin half particles. So the physical system or the physical initial state can be represented by a set of spins. For example, in the Z basis, they are just up, up, down. And in the quantum simulator, maybe can be, for example, they can be labeled by the numbers 1, 1, 0. So 1 is the basis state representing the spin up, and 0 the spin down. Now, since any unitary operation can be written in terms of universal quantum gates, it follows that in principle anything can be simulated. And this is the idea of the so-called digital quantum simulation. Now, this statement is based on a theorem, that has to do with essentially quantum information theory, that states that universal gates can be obtained just in terms of single and two qubit gates. And if you're interested, you can just have a look at the book of Nielsen and Chuang that proves this quite nicely. Now, after we do that, we want to implement basically essentially propose some examples. The initial state can be either a spin state, a state of polarized fermions, for example, bosons in a BEC or fermions in a BCI state, and then apply time evolution. The universality of digital quantum simulator guarantees that any type of Hamiltonian that can be written in terms of these spin operators can be in principle realized in terms of single and two qubit gates. So as just a very standard and simple example, I took the case of an Hamiltonian, which is just the product of 3 sigma z operators. So it's a three-body interaction between 3 spins, among 3 spins. This is an example that you can also find in the book by Nielsen and Chuang. This is quite straightforward. And I would like to leave this sort of exercise to you guys if you want to do it by tomorrow or by Friday. Which is, but I want to give at least a hint on how to do that. So the idea is to represent the time evolution given by this Hamiltonian H in terms of essentially a unitary evolution on an ancilla qubit. So you see that we represent the state of this spin 1, spin 2, and spin 3. And this is an ancilla qubit, so it's sort of an additional qubit that you add in order to be able to represent this three-body operator just in terms of one single and two-body, single and two qubit gates. And in particular, the idea is to prove that the evolution suffered by these 3 qubits under this Hamiltonian here can be represented as a sequence of 6 control knot gates that act respectively of each one of the qubits and the ancilla qubit, plus an intermediate unitary evolution just on the ancilla, which acts as again as a sigma z on the ancilla state. And so the basic idea is that the product of these operators act classically on the 3 qubits in the computational basis. And by the computational basis, again, and here I mean just a spin up and spin down, if you wish. Then the parity of the state of a state for the 3 qubits can be stored in the ancilla, and that we propagate the ancilla, the state of the ancilla, and then erase the parity from the ancilla and provide the final result for the evolution of our initial 3 qubit state. So just do it, just an application of this, the definition of the control knot. And if you are not familiar with that, again, I suggest that you just look at the definition either in the Nielsen and Chuang or even by in Wikipedia, you will find it quite immediately. Okay, so the next step, of course, is try to generalize this to a more complicated or more complex type of evolution or Hamiltonians. In particular, a generic Hamiltonian can be written as a sum of m terms. This is for an arbitrary number of qubits, of course. And HL, as we said, can be either made of single or 2 qubit gates, or can be mapped into single qubit gates, or even more complicated processes that, nevertheless, by the universality of quantum, by the universality concept that we explained before, can be recasted in terms of single and 2 qubit gates. Now, if all the terms, basically of this Hamiltonian commute, then the dynamics is somewhat trivial, because the unitary evolution can be just written as the product of exponentials of each one of the terms. However, if they do not commute, the dynamics is intrinsically non-trivial. Think the simplest case is just a single particle in an external potential V of x. So you have 2 terms, p squared over 2m, which is the kinetic energy, and V of x, which is the external potential energy. The 2 terms do not commute, so you cannot just exponentiate and just apply the product of the 2 exponentials to obtain the dynamics, to study the dynamics of the system. And this is due to the fact that we have the so-called Baker-Campbell, that it holds the so-called Baker-Campbell-Hausdorff theorem. So this is true in principle for an arbitrary amount of time, but if we reduce the amount of time of our evolution to a very tiny time step, then in principle we can apply the so-called trotteization scheme, or essentially make use of the so-called Suzuki-Trotter formula that guarantees that when the number of time steps goes to infinity and the amount of the time steps, or the length of the time step, goes to 0, so here we see t over n, which is a small number in the limit where n goes to infinity, the product of these exponentials essentially reproduce the initial, the exponential of the sum of the 2 operators A and B, which in principle do not commute. So this is a good procedure. Of course, in practice, you cannot have an infinite number of time steps. What you do, you discretize your time, and then you perform a certain error that typically scales like delta t over delta t squared, and you can make it better, I would say, if you use types of higher order algorithms to guarantee that the dynamics is even that converges even better to the original propagator. Okay, that's it for the time evolution. Then one has to ask what happens with the measurements, which is actually the last step of our quantum simulation process. So in principle, one would like to perform a full state tomography, which is unfortunately available only for a few particles or few qubits. But in general, we are only interested in some properties of our quantum system. And in particular, we can, for example, try to map global or some local variables, like, for example, some average correlations, or the local or global magnetization of a spin system, for example. And for that, in general, you don't need to access to the full density matrix of your system. Now, in the analog quantum simulation, what you do is essentially to apply the original idea by Feynman by mapping a physical system to another physical system that you can control with a very high precision. Let me just make an example which probably will clarify this type of statement even more and try to differentiate with respect to the concept of digital quantum simulation that we were discussing before. Suppose that you take that you want to study a sort of paradigmatic model both in statistical physics and in condensed matter, which is called the Bose-Hubbard Hamiltonian, that basically consists of three terms, or can be recasted in terms of three terms, that we will write as an hopping term, a dagger I, aj, which tells us that basically particles can hop from the site j to the site I with an amplitude j. There is a local term, epsilon j, that is multiplied by the number of particles that sit on that site I. And in principle, this epsilon j can either be uniform or even satisfy sort of, that can be extracted randomly from a certain distribution. In this case, we would sort of simulate the physics of disordered systems associated, for example, to Anderson localization, or more recently to many-body localization, etc. And finally, there is an interaction term that is whose strength is proportional to this term u, and basically contains the product of the densities at a certain site I. So for simplicity, we are just taking the simplest Bose-Hubbard model that where essentially the interaction is just a contact interaction. And another important thing is that if we want to call it the Bose-Hubbard model, this operator A, J, and AI should satisfy the usual bosonic commutation relations. In particular, if you want to make it fermionic, what would be the sort of immediate extension? Well, these operators AI should satisfy anti-commutation relations, and typically, if we have spinful fermions, we would need to add an additional index here that would take into account up and down spins. And if I understood correctly, you already have a couple of lectures by Thereza basically explaining in much more detail the physics of the Fermi-Hubbard. So I really don't want to make any additional statements that Thereza could have explained much better than me. The interesting thing now that I want to make is really to make a connection with the quantum simulation side, which means taking this Hamiltonian and try to map it into a realistic physical system, which should be highly controllable. So this sort of proposal was realized back in the early 2000s by the group of Tilman Hensch, Manuel Bloch, Markus Greiner, etc., that were able essentially to map this statistical physics and condensed matter Hamiltonian into an ensemble of bosons that hop on an optical lattice. So you see here the physical particles represented by these purple dots. They can hop from one site to the nearest neighbors in this case in a relatively simple square lattice. In particular, you can have either uniform or non-uniform on-site energies, and then you have interaction. So the interaction actually takes place when two particles sit on the same site. Okay. Now the interesting thing is that you should be able to map the microscopic properties of the physical system under study, in particular this ensemble of bosons in an optical lattice, into the parameters of the original model. So, for example, the hopping amplitude is associated to the localization of the Vanier functions in each one of the lattice sites, and therefore, depending on the localization of these Vanier functions depend on the height of the optical lattice. The interaction strength depend instead on the interaction properties between particles. In particular, it can be recasted, this parameter u, in terms of what is called the scattering length that I will discuss later on during my presentation, or if we don't have time, probably tomorrow. So the important thing is that there is a way to map the microscopic parameters of the physical system into the idealized system that eventually we want to study. So that's the basic idea of a digital quantum simulation. And finally, let me just give you a quick list of the third type of quantum simulation that we can perform by essentially using numerical algorithms that are inspired by quantum information processes. So, for example, the simplest one is the so-called the use of matrix product states that are useful for one-dimensional systems and find application in the so-called DMRG or density matrix renormalization group, which has also a sort of two-dimensional extension by the use of more advanced projected entangled pair states. Then, of course, there is a quantum Monte Carlo. You probably had already some introduction by Thereza earlier. Then there are other techniques such as neural networks, optical control algorithms, and finally variational quantum algorithms that actually include some of the techniques that you can see here. And here I just wanted to show you a sort of schematic view of how variational quantum algorithms actually are useful for, and also how they can be sort of really pictorially schematized. So essentially in the input side, you see you have a sort of trained set of quantum states that can be operated in such a way to obtain a number of cost functions here that you see. This is a structure very similar to a neural network. And finally, by using a certain ansatz that depends on certain parameters theta, you want to you end up with by computing with this quantum computer, quantum simulator, a cost function that depends on this function f of k, and then you plug the result of this cost function into a classical computer that optimizes the parameters and loops again, continues these loops until you find out an optimal quantum state, probability distribution, etc. And you see here the types of applications. Among the applications, you have either really truly quantum computational tasks, such as error correction or compilation of certain types of quantum software, but you also have sort of dynamical simulations, finding the ground states for quantum chemistry processes or condensed matter, and also mathematical application or combinatorial optimization problems. Okay, so now let's be a little bit more specific on the types of platforms that are useful for quantum simulation. And we have really a large number of platforms that can span from arrays of quantum dots to polar molecules, neutral atoms, which are actually the subject also of this school, arrays of trapped ions or cavities, nuclear spin, and superconducting qubits. And the interesting thing is that even though we are talking about this many platforms, also every platform can be actually manipulated in different ways. So for example, atoms can be arranged in lattices, but you can also trap these atoms or play with the atoms in cavities or on certain substrates. This happens also for ions and of course for electronic systems. And each one of the platforms has certain strengths and weaknesses that are sort of summarized here. There have been, of course, a lot of developments since, over the past few years. So some weaknesses that by 2014, for example, were considered a sort of bad way or bad point for example, for neutral atoms, nowadays probably they are not so anymore. For example, now neutral atoms can also, to a certain extent, individually controlled and read out, for example, by using optical tweezers. And I will show you a slide, a sketch in a moment. Now, what are they useful for? We already briefly mentioned that in the previous slides, but let me give you a sort of more detailed overview. So regarding condensed matter systems, one can simulate Haber models, spin models, quantum phase transitions, spin glasses, disordered systems, or frustrated systems, and those who are interested into fermions, for example, ITC superconductivity, BCS and BC crossover, or even topological properties. And then applications also in high energy physics, such as the simulation of Dirac equations or lattice gate theories, and more to the quantum chemistry side, the calculation of thermal rate calculations, molecular energies, chemical reactions, etc. And there are also more recent applications to quantum chaos and also quantum thermodynamics, which is very well developed, for example, in Brazil, in the Brazilian community. Okay, so given that, now we want to focus even more on a subset of these quantum simulators, which are associated essentially to ultra-cold atoms. And by ultra-cold atoms, first of all, we need to specify what is the range of temperatures for these systems to be really cold, ultra-cold. Now, typically in our daily life, we're used to some temperatures of the order of few hundreds of Kelvin. And this is, for example, the temperature felt by these penguins here in the Antarctica. But for ultra-cold systems to be actually cold, ultra-cold, we need to really go much lower in temperature, to temperature of the order of nanokelvin or even picokelvin. And of course, as you already heard in the previous lectures, the sort of paradigmatic example of quantum degeneracy that was obtained in 1995 was the realization of Bose-Einstein condensation with dilute systems. That led to the Nobel Prize in Physics in 2001, awarded to Cornell, Ketterle, and Dillon. Now, ultra-cold atoms can be realized with a certain amount of, with a number of nowadays of atomic species. Probably I forgot some of them, but the most important ones are, of course, alkaline atoms, which have a relatively simple electronic structure, and therefore they are quite useful for manipulation with laser cooling techniques. And then there are other atoms, such as strontium and ytterbium, that are two electron atoms that are very useful for meteorological purposes. And then chromium, dysprosium, and terbium, which display long-range interactions due to intrinsic magnetic moment. And why using ultra-cold atoms? Well, because there is a relatively large, good control on the particle numbers. You can play with the temperatures. You saw that the range of temperatures can span from microkelvin to nanokelvin, so even relatively large order of magnitudes. You can tune the interaction and also play with by engineering different types of interactions. You can play with different geometries. Here we see particles in a square lattice, but I will show examples of other types of lattices. You can work with bosons and fermions, or even simultaneously with bosons and fermions to realize mixtures. And finally, last but not least, the realization of these experiments is really orders of magnitude cheaper than certain types of experiments that, for example, you need to implement to study elementary particle physics or cosmological, for example, properties by launching satellites on space. They are, of course, susceptible to external fields. This is just a reminder of the electronic properties of some alkalis. And again, another important feature is that there are different isotopes which can be either fermionic or bosonics, and whose statistics depend essentially on the number of neutrons in the nucleus. I was mentioning that, of course, they are susceptible to external fields. In particular, if you consider the susceptibility to electric fields, you can play with different arrangements of and strengths of laser fields to realize either square lattices or cubic lattices, or even triangular or hexagonal lattices, or even more exotic lattices. You can have access to quantum, to the so-called quantum gas microscope that allows to basically be sensitive not only to the total density of the system, of the spin system that you want to. In this case, I'm talking about the spin system, but we also talk about other types of systems. You can have access to the total density, or by by applying a linear magnetic field, you can effectively remove just one component, for example, the green one, and then have access, have information regarding the position of the atoms of just one species, or by doing the opposite of the other species. So it is a sort of spin, single site, single spin detection technique. And this has already been developed in several groups around the world. And finally, let me also mention that you can now play with tightly focused laser fields to basically implement, which are called optical tweezers, where you can indeed trap one particle per lattice site, and you can realize these nice patterns, and also realize hearts in 2 dimensions, or even the Eiffel Tower in 3 dimensions, or even more exotic types of patterns, if you wish. Okay, with this, I think before going on, which has to do with interactions, which would actually make the connection to the second part of the topic, of the topics that I would like to cover, basically the difference between short-range and long-range interactions. I think it is probably time to stop. It's already noon there in Brazil. I think that I was able to cover essentially this very broad overview on quantum simulators. And in the next 2 lectures, then I will first try to make clear the distinction between short-range and long-range interactions, what we mean by long-range interactions in the case of ultra-cold atoms, and what I mean by long-range interaction in statistical physics. And then I will start discussing some specific platforms, namely the polar system and the Rydberg atoms, with some applications. And with this, then I would like to conclude. So thank you very much for your attention. And of course, if you have questions, please feel free to ask it. Thanks a lot.
Thank you, Tommaso. Questions? I don't see any. Lucas has a question.
Hi, Tommaso. Thanks for the wonderful lecture. Hi.
I cannot see you, but I can hear you.
Okay.
I see the audience, but I don't see you, but it doesn't matter.
Maybe they're switching the cameras now.
Okay.
Okay. So I do quantum Monte Carlo, which you called, quantum inspired, but it's a classical. Can you see me now?
No, I cannot see, but I know you and I recognize your voice.
Okay.
Don't worry, Lucas. You can go ahead.
So it's a classical algorithm run on a classical computer to solve a quantum problem. So
Right.
my question, maybe it interests people here in the audience and your collaborators, is given the progress of quantum simulation, when do you expect me to be unemployed?
Very good question. No, the thing is that, as you can, probably the message that I should stress a little bit more is that there is work for everyone, both the theorists and the experimentalists. So, of course, I was probably more interested in, when I talked about analog quantum simulation, to emphasize the experimental developments, including, for example, this picture here, this slide that I'm showing right now. Of course, it's very much of the progress that we saw over the past, I would say, 20 to 30 years was experimentally driven. But there was also a lot of theory done on for those systems, and also are related to that. I know that you study not only ultra-cold atoms, but, for example, systems in condensed matter. So, there is really work for everyone. Now, in terms of the third type of quantum simulation, which is the one related to the algorithms, for example, that part started, I would say, with theory. So if your question was, look, there will be quantum computers or will be quantum simulators, I would say, look, wait a second, because there is a lot of connection between theory and experiments. So I don't know if I answered precisely your question. So I actually didn't get why you mentioned Quantum Monte Carlo specifically, but Quantum Monte Carlo, I would say, just a technique that among many others that allow us to study a specific type of many body problems. You can study a single particle to a few hundreds of particles typically. Of course, the question is how scalable is this technique is. Again, there are some strengths and weaknesses for each one of those algorithms that you saw. In my understanding, there are some certain techniques that are very useful for one or two-dimensional systems, maybe at zero temperature. If you already go to finite temperature, maybe you have an edge with Quantum Monte Carlo, or at least with some algorithms in Quantum Monte Carlo. But then, for example, with Quantum Monte Carlo, maybe you cannot address dynamics. So you see, you really need to work together with other, in connection to other groups and with other, you performing different tasks and employing different techniques to really address the number of questions that they really put on the table and they didn't have first time to discuss more in detail.
Oh, thank you, Tommaso. It was more thought-provoking, my question, but I liked the answer.
I know. Thank you, Lucas.
Arnaldo, please.
Hi, Tommaso. Can you hear? Hello? Tommaso?
Yes.
Is Arnaldo? Hi, how are you?
Yes. Oi. Hi.
So my question is, first of all, I want to recall that before we have the present digital computers, we have analog computers, analog classical computers. That you have, for instance, you have resistors. Probably students never have seen this, but I have worked with one of these. You have resistors, capacitors, so as you can simulate, you make these resistors physically, you plug them and you can simulate, for instance, a mechanical system. And this was prior the digital computer. There was the analog classical computer for doing simulations, and you can do nonlinearities also with this. Anyway, so what we have seen is a transition from the analog classical computer to the digital computer. And now I have seen that when you make these qubits, you somehow have these qubits is somehow look like a digital, let's say, somehow it's a digital computer. That this quantum computer can solve, for instance, the Schrödinger equation, the continuous Schrödinger equation, because you are representing qubits. Can it solve continuous Schrödinger equation also? Can you map these qubits to solve the continuum case, for instance, to solve the harmonic oscillation, to solve the many-body in the continuous case, not only in the qubit sense? Can it be mapped to solve? Well, of course, you are losing some information. As in digital computer, you lose some information to make to go to the continuum. So this is my question.
No, it's a extremely important question, and it's actually has to do also with the actual limitations that we have on both on the number of qubits and the controllability of these systems. So nowadays, a concept that I didn't have time to explore in detail, of course, for time constraints, is the so-called NISQ or noise intermediate quantum scale simulators or quantum scale computers, which has to do with the fact that precisely that every platform that I mentioned has some strengths and weaknesses. So, for example, now you can have quantum hardware maybe with a few hundreds of qubits, but depending on the task that you want to solve, like for example, I would say there are some sort of paradigmatic examples like factorization problems, or nowadays what relevant algorithm is the so-called boson sampling, etc., which are more related to quantum information tasks, require a certain number of qubits and the controllability on those qubits. Now, the question that you are asking has two different answers, if you want, because one could play on one side with the development of some certain numerical techniques to solve, for example, the Schrödinger equation. And if you talk about a single particle, that's not an issue anymore, because with the laptop with which I'm doing the presentation, we can solve that equation quite easily and quite quickly. Now, of course, if you want to scale the number of particles on which basically you want to study the time evolution, then maybe my laptop is not useful anymore. You need a cluster. And then the question is, okay, but with a cluster, how many particles can you simulate? Maybe you can simulate, I don't know, by doing a quantum Monte Carlo, let's say 500 or 5,000 particles at most. And therefore, you are limited with certain types of hardware by to few thousands of particles. Now, if you want to move to tens of thousands or even hundreds of thousands, then you need to use a different platform. And then the question is, to which extent that platform is as controllable as your laptop or the cluster on which you run simulations. So I think this is still, there is no straightforward answer for that. If you ask me if you can simulate the Schrödinger equation on a quantum computer, I would say technically you can write an algorithm that allow you to use to solve the Schrödinger equation. Now the question is, how complicated is that Schrödinger equation? And I think depending on on the amount of information that you want to store and evolve in time, then you need to be very careful on which platform you want to use. I think that right now we don't have the resources, for example, to study the quantum dynamics, the exact quantum dynamics of 5,000 particles, for example. So if you want a sort of trivial answer, this is my answer, but I think one really need to be very careful on the type of problem that one need to tackle. But in the perspective, of course, would be to really employ a larger number of qubits in the next future to be able to solve computationally hard problems, like, for example, problems in, as we are interested now in quantum dynamics, but also, for example, in quantum chemistry, to realize new types of drugs and commercialize them much faster than you would do with just by working in the lab. So there are some nice developments in this field, in this direction, for example, by the DeepMind group that is part of Google, if I'm not wrong, that are useful, that are tackling exactly this problem of designing new drugs. And for that, you need the algorithm and you need computers and technology really to do the most or the best that you can do.
Okay.
I don't know if I was able to answer. It was a very general question, I think.
Okay. Thank you.
Okay, we are reaching. We have final question then.
Hi, Tommaso. My name is Bruno. You mentioned the process of translating a Hamiltonian of your problem to a toy model, and that process is, and in other when you were answering other question about the kind of problem that you can solve, you mentioned when you have a complex system, maybe it's hard to try to simulate it with qubits and simulating this in this way. But maybe when I try to simulate a simple system, I don't know, a simple system for a student, a free particle, maybe it's hard to translate that to a Hamiltonian that works on qubits and all. And so maybe the question of complexity is not so direct in my mind. Can you talk something about that, of translating? What is complex to translate to qubits and what we can work? What can we simulate now? Because for me it's like a type of problem that you can maybe translate to quantum gates and so on.
I agree with you. Okay, thanks a lot for the question. So maybe I can try to be a little bit more specific. So I would say there are certain types of tests that are quite immediate. For example, if you want to manipulate the single qubits, this is quite sort of, or if you want to, for example, operate terms of the type, let's see, local magnetic fields. So a local magnetic field applied to a certain set ensemble of spins. Then what you will need are just the manipulation of by applying Pauli operators on single qubits. Okay. Now the question is, suppose that you want to, and that's some sort of straightforward because you just need single qubits. Now, if you want to make things a little bit more complicated, you can think about realizing sort of long-range interactions between different qubits. So, for example, a term like the polar interaction between site I and site J, which are arbitrarily distant. Now, the question is, how would you do that? Maybe without affecting other spins in the middle. If you are, for example, in 1D or in 2D, that may be relatively complicated. So one possibility would be to take these two qubits, make them move them sufficiently close by, do the operation between them, and then move them apart. So it looks crazy, but it actually can be in principle done with optical tweezers. So precisely the setup that I'm showing you right now. Now, there are more difficult tasks. For example, the many-body interaction that I was showing you as an example before, where you had a three-qubit system, and the Hamiltonian, which was the product of sigma Z1, sigma Z2, sigma Z3. So you see that already to implement that type of three-body Hamiltonian, you need instead not only 3 qubits, but you need 4 qubits. So the 3 physical qubits plus an ancilla qubit. On top of that, you need to realize essentially 7 operations. So you have 6 CNOT gates plus an intermediate unitary evolution on the ancilla. Now you can sort of speculate on the complexity of this process and try to mimic what would happen when you have maybe n qubits, so an n-body interaction. And that n-body interaction maybe does not involve only sigma Z operators. So you already see that the complexity of the algorithm that you need to devise in order to develop that type of interaction, and not only the interaction, but also the time evolution with that interaction, really scales, becomes more and more complex, the larger the number of qubits that you are involved in. And we are still talking about only spin systems. Now you can rephrase this question, for example, and trying to solve another problem, maybe a problem in quantum chemistry or a basic quantum mechanical problem, like solving the hydrogen atom. Okay, solving the hydrogen atom means computing the spectrum of the hydrogen atom, or at least the spectrum of the bound states. Okay, so now for this question, to solve this question, which is sort of similar to what Arnaldo asked before regarding the harmonic oscillator, you would need to discretize space first if you want to implement in a digital way. Okay, digital way, you need to discretize, define the proper variables, and then define the algorithms. Okay, to basically solve the problem that you want to solve and to study. In this case, maybe solving the spectrum is not equivalent to computing the dynamics. So it's really a different task, but that different task also needs some specific or some very peculiar type of algorithm. So in this respect, what I think there is no general answer. One should really sit down and try to first define the question, and then once you define the question, try to find a method to implement that problem into, or to map the problem into the digital quantum simulator. Again, I say this is not a straightforward, not necessarily a straightforward way. Sometimes, if you just sit down and try to do it on your classical computer, things are much easier. Sometimes you can also do with your pen for example, you can solve analytically the spectrum of the hydrogen atom. Okay, so you don't really need to be careful on what I told you today. I'm not trying to sell anything in terms of computational power. So this is not the case. I'm just saying that the perspective is that you can solve in principle some problems that right now you cannot really properly address with the current techniques.
Okay, thank you, Tommaso. Let's thank Tommaso again.
Thank you very much, Emmanuel.
We are looking forward to hear you again tomorrow. So we leave for lunch now and we restart at 2 p.m. Thank you.